Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're going to drift gently through a question that sounds simple at first, yet becomes more fascinating the longer you sit with it. Where exactly are we in the Milky Way? Not just Earth, not just the solar system, but us, our little neighbourhood of stars floating somewhere inside a galaxy so large that even light takes tens of thousands of years to cross it. For most of human history, we looked up at the pale, cloudy band of the Milky Way and imagined it as a distant decoration, a faint river of light painted across the night. It didn't feel like a place we were inside. It felt like something far away. Only recently, in the scale of human history, did we begin to realise that this glowing arc is not scenery. It is home. And now, with the James Webb Space Telescope peering through curtains of dust and distance, astronomers are beginning to refine our address in the galaxy with a clarity that would have seemed impossible even a decade ago. It turns out we're not quite where we once thought, or at least not in the way we once pictured it. Our position, our surroundings, even our understanding of the structures around us are becoming sharper, richer, and more detailed. But we'll move slowly tonight. There's no hurry in understanding something as large as a galaxy. Ideas like this are best approached the way you might approach a quiet shoreline at dusk, step by step, letting your mind adjust to the scale. Before we go further, I'd like to ask you something gentle and simple. Where are you listening from tonight? Not just the city or country, but the setting. Are you in a dim room with the lights low? Are you under a blanket, perhaps with the faint glow of a screen lighting the ceiling? Maybe there's the soft hum of a heater, or distant traffic, or just the quiet presence of the night itself. And what time is it for you right now? It's a fitting question, really, because while we think about where we are in space, we're also always somewhere in time, each of us occupying our own small moment, listening to the same words from different corners of the world, different hours of the night. If you find this journey soothing, or interesting, or simply a pleasant way to unwind after a long day, I'd be grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of the internet reach others who might need a quiet place to rest their thoughts for a while. Now, let's begin easing into the story. Picture the night sky as our ancestors saw it, long before telescopes, long before photography, long before anyone imagined that the faint smear of light overhead was made of hundreds of billions of stars. To the naked eye, the Milky Way looks like a mist, a pale band stretching from horizon to horizon on the darkest nights. Many cultures imagined it as a road, or a river, or a trail of something spilled across the sky. The ancient Greeks thought of it as milk scattered by the goddess Hera. In parts of Asia, it was seen as a celestial river separating lovers who could meet only once a year. To some indigenous cultures, it was a pathway of spirits, or the backbone of the night. None of these interpretations were scientific in the modern sense, but they captured something true in their own way. The Milky Way does feel like a landscape when you look at it carefully, not a flat surface, but something with depth and texture, brighter patches, darker lanes, a sense of layers overlapping, and yet for thousands of years, no one knew what it really was. It wasn't until the early 1600s, when Galileo Galilei turned a small handmade telescope toward that pale band, that the first real clue emerged. Through the lens, the mist resolved into countless faint stars, far too many to distinguish with the naked eye. The Milky Way wasn't a cloud at all, it was a swarm. That realization alone was astonishing, but it raised a deeper question. If the Milky Way was made of stars, where were we in relation to it? Were we near the center of this swarm, or somewhere off to the side? Was it small or unimaginably vast? For a long time, no one could answer. Part of the difficulty comes from a simple, almost humorous problem. Imagine trying to map a forest while standing inside it. You can see the trees around you, but the overall shape of the forest, its edges, its clearings, its structure, are hard to grasp. From inside, everything looks like trees in all directions. That's our situation in the Milky Way. We're embedded within it, surrounded by stars, gas and dust. We don't have the luxury of stepping outside and taking a photograph, the way we can with distant galaxies, so astronomers had to become detectives, piecing together clues from brightness, motion, colour and distance, slowly building a picture of the galaxy from the inside out. Even the size of the Milky Way was once a matter of debate. In the early 20th century, some astronomers believed our galaxy might be the entire universe, a single vast island of stars with nothing beyond it. Others suspected that the faint spiral smudges seen through telescopes, objects we now know are other galaxies, might be distant systems like our own. It took decades of observation, argument and careful measurement before the true scale of the universe began to emerge. And as that picture expanded, something else became clear. We are not at the centre. That realization, when it first took hold, was quietly humbling. Humanity had already gone through similar shifts before. First, we learned that Earth is not the centre of the solar system. Then we learned that the Sun is just one star among many. And then we learned that our galaxy is just one among billions. Each step moved us a little farther from the centre of things, but also, in a strange way, brought us closer to understanding reality as it truly is. Now, the James Webb Space Telescope is helping us refine one more piece of that puzzle, not just the scale of the galaxy, but our exact position within it and the nature of the region we call home. To appreciate what Webb is revealing, it helps to pause and think about the scale we're dealing with. Our solar system, from the Sun to the outer reaches of the Oort cloud, is already enormous by everyday standards. Light from the Sun takes 8 minutes to reach Earth. That same light takes over 4 hours to reach Neptune. And yet, this entire region is just a tiny dot within the Milky Way, smaller than a grain of sand compared to a continent. The nearest star beyond the Sun, Proxima Centauri, is over 4 light-years away. That means the light entering a telescope tonight left that star more than 4 years ago, before some listeners began new jobs, moved homes, or changed the routines of their lives. And even that distance is small on the galactic scale. The Milky Way itself is about 100,000 light-years across. If you could travel at the speed of a light, the fastest speed allowed by physics, it would still take you 100,000 years to cross from one side to the other. Trying to picture that distance can feel almost slippery, like trying to hold water in your hands. So sometimes it helps to shrink the scale in your imagination. If the Milky Way were the size of North America, our solar system would be smaller than a coin. Not a city, not a building, not even a room. A coin. And somewhere within that vastness, we're orbiting the centre of the galaxy, moving together with millions of other stars in a slow, graceful journey that takes about 230 million years to complete a single circuit. That means the last time Earth was in this exact position in its orbit around the galaxy, dinosaurs had only just begun to appear. Continents were arranged differently. The world itself was almost unrecognisable. Right now, without feeling it, without noticing it, you and I and everyone listening are travelling through space at about 220 kilometres per second, carried along by the Sun's orbit around the galactic centre. It's a curious thought, isn't it? We often think of ourselves as still, sitting in a chair or lying in bed. But in reality, we are moving at extraordinary speeds, drifting through the galaxy together. And yet, despite all this motion, the night sky looks calm and unchanging, because the distances are so vast that even enormous speeds translate into only tiny shifts over a human lifetime. For a long time, astronomers believed they had a reasonably clear picture of where we are in the Milky Way. We were thought to reside in a minor spiral arm, or perhaps a spur, located between two larger arms, the Sagittarius arm and the Perseus arm. This region, often called the Orion arm or Orion spur, seemed to be a kind of galactic suburb, not near the crowded centre, but not at the extreme edge either. That picture, broadly speaking, still holds true, but the details, the fine structure, the precise arrangement of gas clouds, star-forming regions and clusters are being refined in ways that are changing how we understand our surroundings. This is where the James Webb Space Telescope enters the story. Unlike optical telescopes that see primarily visible light, Webb is designed to observe infrared light, which can pass through clouds of dust that block ordinary starlight. And dust, it turns out, is everywhere in the Milky Way. Enormous dark lanes of it thread through the spiral arms, hiding entire regions from view. To earlier telescopes, many parts of our galaxy were like rooms behind closed doors. Webb is beginning to open some of those doors. Through its observations, astronomers are mapping star-forming regions in unprecedented detail, tracing the structure of nearby spiral features and measuring distances with greater precision. These measurements help refine our map of the galaxy, not in dramatic headline-grabbing shifts, but in careful adjustments that make the picture clearer, sharper, more accurate. And there is something quietly beautiful about that process. Science often advances not through sudden revolutions, but through steady improvements in clarity, like adjusting the focus of a lens. As the map sharpens, our sense of place sharpens with it. We are beginning to understand not only where we are, but what kind of neighbourhood we inhabit, what kinds of stars surround us, how often new stars are born nearby, and how our region fits into the broader structure of the Milky Way. All of this helps answer a question that humans have been asking, in one form or another, for as long as we have looked at the sky. Not just what is out there, but where are we within it? And that question, simple as it sounds, has layers. Because understanding our place in the galaxy is not only about coordinates and distances, it is also about perspective. When you step back and see how vast the Milky Way is, and how small our solar system is within it, everyday concerns can feel a little lighter, a little less heavy. Not insignificant, not unimportant, but set within a wider context. There is something calming in that, I think. A reminder that we are part of something enormous and ancient, something that was unfolding long before we arrived and will continue long after. If you step outside on a clear, dark night far from city lights and give your eyes a few minutes to adjust, you may notice something curious about the Milky Way. It doesn't look like a vast, three-dimensional system of hundreds of billions of stars. It doesn't look like the majestic spiral galaxies we see in photographs from telescopes. Instead, it appears as a soft, pale band stretching across the sky, almost like a faint cloud or a streak of mist. It looks flat. That impression is so natural, so intuitive, that for most of human history people assume the Milky Way really was some kind of luminous ribbon or distant veil. It seemed to hang above us, like a ceiling decoration, rather than surrounding us in all directions. Even today, when we know intellectually that we live inside a galaxy shaped like a flattened disk, the view from Earth still gives the strong impression of a narrow strip rather than an enormous enveloping structure. So why does it look that way? To understand this, it helps to imagine yourself standing in a forest again, but this time not just anywhere in the forest. Imagine the forest stretches for thousands of kilometers in every direction, and the trees are arranged mostly in a broad, thin layer, like a gigantic sheet of woodland spread across a plain. Now imagine standing right in the middle of that sheet. If you look along the plane of the forest toward the horizon, your line of sight passes through tree after tree after tree, mile after mile of trunks overlapping in your view. The forest appears dense and thick in that direction, but if you tilt your head upward, looking out of the plane of the forest, your line of sight quickly leaves the layer of trees and enters open sky. In that direction, the forest appears sparse or even empty. That difference, the contrast between looking along the layer and looking out of it, is exactly what shapes our view of the Milky Way. Our galaxy is not a sphere of stars evenly distributed in all directions. It is a flattened disk, about 100,000 light-years across, but only about 1,000 light-years thick in most places. That means most of the stars are concentrated in a relatively thin plane, and we happen to live right inside that plane. When we look toward the plane of the galaxy, our eyes trace a path through vast numbers of stars packed together along the disk. all that distant starlight blends into the luminous band we call the Milky Way. But when we look above or below the plane, there are far fewer stars in those directions, so the sky appears darker and more empty. The Milky Way isn't actually a band in space. It's a band in our perspective. This is one of those ideas that sounds simple once you hear it, but it took centuries for astronomers to fully understand. Before telescopes, the Milky Way was mysterious. It looked like a cloud, but it didn't move like clouds do. It stayed fixed relative to the stars night after night, year after year. Some ancient philosophers even speculated that it might be made of countless tiny stars too faint to see individually. That idea was remarkably close to the truth, but it remained speculation until Galileo turned his telescope toward it in 1609. Through his small instrument, the mist resolved into innumerable stars, far more than anyone had imagined. The Milky Way was not a cloud or vapour. It was a crowd. That discovery was profound, but it still didn't answer a deeper question. Why were those stars arranged in a band rather than scattered evenly across the sky? At first, no one knew. It took generations of observation and careful measurement before astronomers began to realise that the band shape was a clue about the structure of the galaxy itself. But even today, there's another layer to the illusion, one that's easy to overlook. The Milky Way doesn't just look flat. It looks uneven, mottled, streaked with dark gaps and bright patches. Some sections glow intensely, while others seem to fade or disappear altogether. Those dark regions are not empty space. They are clouds of dust. Interstellar dust is made of tiny particles, grains of carbon, silicates, and other materials floating between the stars. These particles are incredibly small, smaller than smoke particles, but there are so many of them spread across vast distances that they can block or scatter starlight, creating dark lanes that cut across the Milky Way's glow. When you see those jagged, shadowy streaks in the Milky Way, you're not seeing gaps in the galaxy, you're seeing curtains. Behind those curtains lie stars, clusters, and entire regions of space that visible light cannot easily reveal. This is one of the reasons mapping our galaxy has been so difficult. We're trying to understand a structure from inside it, while much of it is hidden behind drifting veils of dust. It's a bit like trying to map a city while walking through it in thick fog. You can see the nearby buildings clearly, but distant neighbourhoods are obscured. Streets seem to vanish into the mist. Shapes become uncertain, and yet the city is still there, stretching far beyond what you can see. For centuries, astronomers were limited to visible light, and their maps of the Milky Way reflected that limitation. The galaxy appeared smaller, patchier, and less structured than it truly is, because large portions were simply invisible to their instruments. Only with the development of radio astronomy, infrared telescopes, and now the extraordinary sensitivity of the James Webb Space Telescope have we begun to see through the dust and refine the picture. But before we get to that, there is another reason the Milky Way looks flat, and it has to do with the way our eyes and brains interpret brightness. The human eye is not very good at perceiving depth in the night sky. During the day, depth cues are everywhere. Shadows, perspective, motion, familiar objects all help the brain judge distance. But at night, stars are just points of light. A bright star might be relatively close, or it might be enormously distant but intrinsically luminous. A faint star might be small and nearby, or huge and far away. Without reliable depth cues, the brain tends to interpret the sky as a kind of dome, a surface at a fixed distance. The stars seem pinned to that dome, and the Milky Way appears painted across it. This is a powerful illusion, and it persists even when we know better. Even professional astronomers, when they step outside and look up with the naked eye, still experience that sense of flatness. Knowledge doesn't erase perception, it simply adds another layer of understanding beneath it. There's also something else quietly shaping our view, something so familiar that we rarely think about it. The rotation of the Earth. As the Earth turns, the Milky Way appears to rise and set, arching across the sky in different orientations depending on the time of year and your location on the planet. Sometimes it forms a vertical pillar rising from the horizon. Other times it stretches like a luminous bridge overhead, but in every case, it remains a band. That band is the projection of the galactic plane onto our sky, the same way the equator of the Earth can be projected onto a map as a line. We are looking outward along the disk, seeing the accumulated light of countless stars compressed into a narrow strip by perspective. If you could travel far above the Milky Way and look down on it, the view would be completely different. You would see a vast spiral galaxy, its arms curving gracefully outward from a bright central bulge, dust lanes tracing intricate patterns, clusters of stars scattered like sparks across a dark background. From that vantage point, there would be nothing flat about it. And somewhere in one of those spiral features, far from the centre but not at the extreme edge, a small yellow star would be orbiting quietly, accompanied by a handful of planets, one of which harbours listeners lying in dark rooms, thinking about galaxies. It's a humbling thought, but also a comforting one. The universe is large, but we are not outside it. We are inside, participants rather than spectators. There's another subtle effect that contributes to the illusion of flatness, and it has to do with scale. The stars that make up the Milky Way's glow are not all at the same distance. Some are a few thousand light years away, others are tens of thousands. Their light has travelled for different lengths of time, through different regions of space, encountering different amounts of dust and gas. All of that light arrives together, blending into a continuous glow. Our eyes cannot separate those layers. We see only the combined effect, a smooth band of brightness, like looking at distant city lights through a haze. The individual sources merge into a single luminous strip, and depth is lost. Astronomers, however, have learned to disentangle those layers using spectroscopy, parallax measurements, and observations at different wavelengths. By studying how stars move, how their light shifts, and how dust absorbs certain colours more than others, they can reconstruct the three-dimensional structure hidden within that flat-looking band. It's a bit like listening to an orchestra from behind a curtain and learning to identify each instrument by sound alone. And this is where modern observatories, including the James Webb Space Telescope, are making a remarkable difference. By observing in infrared light, Webb can peer through dust clouds that once blocked our view, revealing stars and structures that were previously invisible. This doesn't change the fact that the Milky Way looks flat to the naked eye. That illusion remains as gentle and familiar as ever. But behind the illusion, the map is becoming clearer, the depth more defined, the details sharper. We are learning not only that we live inside a galaxy, but exactly how that galaxy is arranged around us. There is something quietly profound about realizing that what looks like a thin band in the sky is actually the edge of a vast rotating system of stars, gas and dust, all bound together by gravity, all moving through space together. And yet, even as our understanding deepens, the view from Earth remains the same. On a clear night, far from artificial lights, the Milky Way still appears as a pale, luminous river, arching silently overhead, as it has for thousands of years. Perhaps that is part of its charm. The universe does not always reveal its true nature at a glance. Sometimes it offers us a gentle illusion first, and only later, with patience and curiosity, allows us to see what lies beneath. And once you begin to see that hidden structure in your mind's eye, once you imagine the disk of the galaxy surrounding you, the next question arises naturally. If we are inside this immense flattened system, how did we first begin to figure out its shape at all? And what clues led astronomers to realize that the Milky Way is not a cloud, not a sphere, but a vast spiral galaxy with a structure far more intricate than anyone once imagined? Long before telescopes floated in space, before infrared detectors and digital sensors, before anyone could even agree on how large the universe might be, there were people patiently trying to answer a deceptively simple question. How many stars are there, and how are they arranged? It's easy now to take for granted that the Milky Way is a galaxy, a vast rotating disk of stars, gas, and dust. But for most of human history, that idea didn't exist. The night sky was a mystery not only in its distance but in its structure. Stars appeared scattered across a dark dome, and the pale band of the Milky Way stretched overhead without explanation. No one knew whether those stars formed a shallow layer, a deep ocean, or something else entirely. The first real attempts to map our galaxy began not with powerful instruments, but with careful counting. In the late 18th century, an astronomer named William Herschel set out to do something remarkably ambitious. He wanted to measure the shape of the Milky Way using the only tools available to him: a telescope, patience, and a methodical approach to observation. Herschel's idea was straightforward in principle. If the stars were distributed in a certain way, then the number of stars visible in different directions should reveal something about the structure of the system. If you looked in one direction and saw many stars, perhaps that direction extended farther into the galaxy. If you looked in another and saw fewer, perhaps the edge was closer. So Herschel began counting. Night after night he pointed his telescope at different regions of the sky and recorded how many stars he could see in each field of view. It was slow, repetitive work, requiring concentration and persistence. There were no computers to assist him, no automated surveys, only the quiet routine of observation, note-taking and comparison. Over time, patterns began to emerge. In some directions, particularly along the band of the Milky Way, the star counts were much higher. In other directions, especially above and below that band, the counts dropped sharply. From this, Herschel inferred something important. The stars were not spread evenly in all directions. They seemed to form a flattened system, wider in some directions than others. Based on his counts, he sketched a rough map of the Milky Way, a flattened, disc-like shape with the sun somewhere near the centre. That last part turned out to be wrong, but it was an understandable mistake. Herschel assumed that his telescope could see all the way to the edges of the galaxy. He didn't know about the vast clouds of interstellar dust that block visible light and hide distant stars from view. Because of that, his map showed a galaxy smaller than the real one, and it placed us near the middle simply because the dust limited how far he could see in every direction. Still, Herschel's work was groundbreaking. For the first time, someone had attempted to map the structure of our stellar system using systematic observation. It was a first draft, imperfect but pioneering, like the earliest maps of continents drawn before explorers had reached every coastline. What's especially striking is how intuitive his method was. Counting stars sounds simple, but it was a powerful way to extract information from limited data. Even today, astronomers sometimes use similar statistical techniques, though with far more sophisticated tools. As the 19th century progressed, telescopes improved, and astronomers began to catalogue stars more precisely. They measured positions, brightness, and gradually motions. Star catalogues grew from hundreds to thousands, then to tens of thousands. Yet the larger picture of the Milky Way remained elusive. Part of the difficulty was scale. Distances between stars are so vast that measuring them directly is extremely challenging. The most basic method, called parallax, relies on observing how a nearby star appears to shift slightly against the background of more distant stars as Earth orbits the Sun. But the shifts are tiny, fractions of a second of arc, far smaller than what early instruments could reliably detect for anything but the nearest stars. Without accurate distances, building a three-dimensional map of the galaxy was like trying to map a mountain range while seeing only silhouettes on the horizon. Even so, astronomers pressed on. They began to notice that stars were not all the same. Some were brighter, some dimmer, some redder, some bluer. Spectroscopy, the study of how light is spread into its component colours, revealed that stars differed in temperature and composition. These differences provided new clues about their intrinsic brightness, which in turn helped estimate their distances. Gradually, the galaxy began to acquire depth in the minds of those studying it. Another breakthrough came from the study of star clusters, groups of stars bound together by gravity. Two main types attracted attention: open clusters, which are relatively young and found mostly in the galactic plane, and globular clusters, which are older, densely packed spheres of stars distributed in a roughly spherical halo around the galaxy. Globular clusters turned out to be especially important. By the early 20th century, astronomers had identified many globular clusters and measured their positions in the sky. One astronomer in particular, Harlow Shapley, began studying these clusters in detail. He used a special class of stars called Cepheid variables, whose brightness varies in a predictable way, to estimate distances to the clusters. Cepheid variables are remarkable objects. Their pulsation period is directly related to their intrinsic brightness. By measuring how quickly a Cepheid brightens and dims, astronomers can determine how luminous it truly is. Comparing that intrinsic brightness to how bright it appears from Earth reveals its distance. It was like having a cosmic measuring stick. Using Cepheids in globular clusters, Shapley calculated distances far greater than anyone had previously imagined. These clusters were not just a few thousand light-years away. Some were tens of thousands of light-years distant. Even more intriguingly, their distribution in the sky was not centered on the Sun. Instead, the clusters seemed to be concentrated in a particular direction, toward the constellation Sagittarius. From this, Shapley drew a bold conclusion. The center of the Milky Way was not near us at all. It lay far away, in the direction of Sagittarius, and the Sun occupied a position well off-center in the galaxy. This was a profound shift in perspective. For centuries, humans had been gradually moving away from the center of things. First, Earth lost its central position in the solar system. Then the Sun lost its central position in the universe. Now, even within our own galaxy, we were not in the middle. We were somewhere out in the disk, orbiting quietly among billions of other stars. Shapley's model was not perfect. He overestimated some distances because he didn't fully account for interstellar dust dimming the light of Cepheids, which made them appear farther away than they were. But his overall picture, a large galaxy with the Sun located far from the center, was essentially correct. Around the same time, another major debate was unfolding, one that would shape our understanding of galaxies themselves. In the early 20th century, astronomers argued about the nature of spiral nebulae, faint spiral-shaped objects visible through telescopes. Were they part of the Milky Way, or were they separate island universes, distant galaxies like our own? This question culminated in the famous Great Debate of 1920 between Harlow Shapley and Heber Curtis. Shapley argued that the Milky Way was so vast that the spiral nebulae must lie within it. Curtis argued that they were separate galaxies far beyond our own. The debate was eventually settled by Edwin Hubble, who observed Cepheid variables in the Andromeda Nebula and showed that it lay far outside the Milky Way. The universe suddenly became much larger, filled with countless galaxies rather than just one. And with that realization, mapping the Milky Way took on new significance. Our galaxy was no longer the whole universe. It was one structure among many, and understanding its shape and our position within it became part of a larger cosmic context. Yet even as astronomers refined their models, many uncertainties remained. Dust continued to obscure large regions of the galaxy. Distances were difficult to measure. Spiral structure was inferred rather than directly observed. It was a bit like assembling a puzzle with many missing pieces, guided by intuition, indirect evidence, and careful reasoning. Still, each generation added little more clarity. By the mid-20th century, radio astronomy opened a new window. Observations of hydrogen gas at a wavelength of 21 centimeters allowed astronomers to trace the distribution of gas in the galaxy, revealing hints of spiral arms and large-scale structure hidden from optical telescopes. These radio maps began to show the Milky Way as a true spiral galaxy, with arms winding outward from a central bulge. The Sun appeared to reside in a minor arm or spur, not one of the major arms, but not in empty space either. The picture was becoming more detailed, more three-dimensional, more alive, and yet, even with these advances, there were limits to what could be seen from Earth. Dust still blocked many regions, measurements still carried uncertainties. The galaxy was vast, and we were still very much inside it, trying to understand its form from within. That is why modern observatories, especially space telescopes operating in infrared wavelengths, are so transformative. They allow us to see through dust, measure distances with unprecedented precision, and map star-forming regions in ways that were once impossible. The James Webb Space Telescope is part of that ongoing effort, refining the map, filling in missing details, and helping us understand not only the structure of the Milky Way, but our exact place within it. It's a continuation of a journey that began with simple star counts, with an astronomer patiently sweeping the sky and tallying points of light. There is something quietly inspiring about that continuity. The tools have changed dramatically, from hand-ground mirrors to orbiting observatories, but the curiosity driving the work remains the same. We still look up and ask, where are we? And as our methods improve, the answers grow clearer, revealing not just the shape of our galaxy, but the intricate structures within it, structures that will soon lead us to another question, one that early astronomers struggled with constantly. How do you measure distances across such enormous darkness? And how do you know how far away anything truly is when the nearest stars themselves are light years beyond reach? By the beginning of the 20th century, astronomers had already begun to suspect that the Milky Way was far larger than anyone once believed, yet there was still one assumption that lingered quietly in the background. Many scientists thought the Sun lay near the centre of the galaxy. It wasn't arrogance so much as a practical conclusion, drawn from the evidence available at the time. If you look around and everything appears roughly similar in all directions, it feels reasonable to assume you are somewhere near the middle. But that impression, like so many first impressions in astronomy, turned out to be misleading. The shift away from that idea began with a careful observer who had a talent for patience and a willingness to trust the evidence even when it led somewhere uncomfortable. His name was Harlow Shapley, and the work he carried out in the 1910s would quietly rearrange humanity's sense of place in the cosmos. To understand what Shapley was trying to figure out, it helps to think about what astronomers already knew. By that time, telescopes had revealed thousands of star clusters scattered across the sky. Among them were globular clusters, dense spherical collections of hundreds of thousands of stars, bound tightly by gravity and shining as compact, luminous swarms. Globular clusters are striking objects even through modest telescopes. Instead of loose groupings like open clusters, they appear as bright, concentrated balls of light, often with a glowing core and a halo of faint stars fading outward. They are ancient as well, some of the oldest structures in the galaxy, formed when the Milky Way itself was still young. Shapley realized something important about these clusters. Because they are so bright and so massive, they can be seen across enormous distances. That makes them useful markers, like distant beacons scattered throughout the galaxy. If he could measure how far away those clusters were, he reasoned, he could map their distribution in space. And if globular clusters surrounded the galaxy in a roughly spherical halo, then their centre of distribution should point toward the centre of the Milky Way itself. It was an elegant idea, but turning it into reality required solving a difficult problem. How do you measure distances to objects tens of thousands of light years away? The answer came from a particular type of star known as a Cepheid variable. These stars brighten and dim in a regular cycle, expanding and contracting like a slow, steady heartbeat. Years earlier, astronomer Henrietta Swan-Leavitt had discovered a crucial relationship while studying Cepheids in the Small Magellanic Cloud. She found that the period of a Cepheid's brightness variation is directly related to its intrinsic luminosity. In simple terms, by measuring how long it takes a Cepheid to complete one cycle of brightening and dimming, you can determine how bright it truly is. Once you know how bright a star really is, comparing that to how bright it appears from Earth tells you its distance. A dim-looking star that is intrinsically bright must be far away. A bright-looking star that is intrinsically faint must be nearby. This method, sometimes called a standard candle technique, gave astronomers a way to measure distances far beyond what parallax alone could reach. Shapley began identifying Cepheid variables within globular clusters and using their pulsation periods to estimate distances. The numbers he obtained were astonishing. Many clusters were far farther away than anyone had previously imagined, tens of thousands of light-years distant. Even more surprising was their distribution. When Shapley plotted the positions of globular clusters on a map of the sky, he noticed that they were not spread evenly around us. Instead, they were concentrated in one direction, toward the constellation Sagittarius. If the Sun were at the centre of the galaxy, globular clusters should have been distributed roughly symmetrically in all directions. But they were not. They formed a lopsided pattern, heavily weighted toward one region of the sky. The implication was clear, though it took time to fully accept. The centre of the Milky Way was not where we were. It lay far away, in the direction where the clusters were most densely packed. Shapley estimated that the centre of the galaxy was about 50,000 light-years away from the Sun. His distance was larger than the modern value, which is closer to about 26,000 light-years, but the essential conclusion was correct. We are not at the centre. We are off to one side, orbiting quietly in the galactic disk. It's hard to overstate how significant this realization was. For thousands of years, humans had imagined themselves at the centre of the cosmos in one way or another. Ancient cosmologies placed Earth at the centre of everything. The Copernican revolution moved Earth away from the centre, but left the Sun in a privileged position. Later discoveries revealed that the Sun itself is just one ordinary star among many. Now, even within our own galaxy, we were not central. We were peripheral, one star among billions, located far from the crowded core. There is a certain humility in that progression, but also a certain clarity. Each step away from the centre brought us closer to understanding the universe as it truly is, rather than as we once imagined it to be. Shapley's work did not immediately convince everyone. Science rarely changes overnight. Some astronomers questioned his distance measurements, and others were reluctant to abandon the long-held assumption that we occupied a central position. Part of the skepticism came from the sheer scale of his results. A galaxy tens of thousands of light-years across seemed almost impossibly large by the standards of the time. Accepting such a vast Milky Way required rethinking many other ideas about the universe. There was also another complication. Interstellar dust, which absorbs and scatters light, was not yet fully understood. Dust makes distant objects appear dimmer than they really are, which can lead to overestimating their distances. Shapley's distances were indeed somewhat inflated for this reason, but the overall pattern he found remained valid. As more observations accumulated, the evidence in favour of an off-centre sun grew stronger. Radio astronomy, infrared observations and later space-based telescopes all confirmed that the galactic centre lies in the direction of Sagittarius, hidden behind thick clouds of dust that block visible light. Today we know that at the heart of the Milky Way lies a dense concentration of stars surrounding a supermassive black hole known as Sagittarius A star. It is a region of intense gravitational forces, high-energy radiation, and crowded stellar orbits, very different from the relatively quiet neighbourhood where our Sun resides. In a way, it is fortunate that we are not closer to the centre. The inner regions of the galaxy are far more chaotic, with higher rates of supernova explosions and stronger tidal forces. Our position, about halfway out in the disk, may be one of the reasons life had time to develop on Earth without being repeatedly disrupted by catastrophic events. That idea, sometimes called the galactic habitable zone, is still being studied, but it highlights an interesting possibility. Being off-centre might not be a disadvantage. It might be exactly what made our existence possible. There is also something quietly reassuring about knowing that our location is not special, in the sense of being central or unique. The universe does not revolve around us, and yet we are part of it in a very real way, orbiting the galaxy along with billions of other stars, sharing in the slow, steady motion of the Milky Way. If you imagine the galaxy as a vast rotating city of stars, the centre might be the crowded downtown, bright and energetic but also intense and hazardous. We live in the suburbs, quieter, more spacious, with fewer dramatic events but plenty of room for stable planetary systems. That suburban analogy isn't perfect, but it captures something of the feeling. Our region is not empty, not remote, but comfortably distant from the most turbulent parts of the galaxy. As astronomers refined their measurements over the decades, the map of the Milky Way became clearer. The Sun's distance from the centre was revised downward as dust effects were better understood. The spiral structure of the galaxy was traced using radio observations of hydrogen gas. Star-forming regions were mapped in increasing detail, and now, with the James Webb Space Telescope observing in infrared wavelengths, we are refining that map even further. Webb is able to peer through dust clouds that once hid large portions of our galactic neighbourhood, revealing stars and structures that help astronomers measure distances and distributions with unprecedented precision. Each improvement adds another layer of clarity, another piece of the puzzle, helping us understand not only where we are in the galaxy, but how our region connects to the larger structure of spiral arms, gas clouds, and star-forming regions. The realization that we are not at the centre was the first big shift in that journey, a turning point that changed how we think about our place in the cosmos. It replaced a comforting illusion with a more complex and more accurate picture, one in which we are participants in a vast system rather than the focal point of it. And once that shift was made, a new challenge emerged. If we are not at the centre, and if distances in the galaxy are so enormous, how do astronomers measure those distances reliably, especially when many stars are too far away for parallax and too obscured for simple brightness estimates? Trying to measure distance in space is not at all like measuring distance on Earth. Here, if you want to know how far away something is, you can walk to it, drive to it, or at least see it clearly enough to estimate its size. Even mountains on the horizon give themselves away through perspective and familiar scale, but in space there are no signposts, no overlapping objects to give easy clues, and nothing to compare against except light itself. When astronomers look into the night sky, they are essentially staring into darkness punctuated by points of brightness, each of which could be nearby and faint or distant and brilliant. At first glance, there is no obvious way to tell the difference. Two stars may appear equally bright, yet one could be hundreds of times farther away than the other, and yet over time, astronomers have developed an entire toolkit for measuring distances across the vastness of the galaxy. These methods are sometimes called the cosmic distance ladder, because each technique works over a certain range, and each one builds upon the previous steps. It all begins with the nearest stars. The simplest and most direct method for measuring stellar distances is something called parallax. The idea behind parallax is wonderfully straightforward, and you've probably experienced it without realizing. If you hold your finger out in front of your face and close one eye, then the other, your finger seems to shift against the background. That apparent shift happens because your viewpoint changes slightly from one eye to the other. Astronomers use the same principle, but instead of switching eyes, they use Earth's orbit around the Sun. 6 months apart, Earth is on opposite sides of its orbit, about 300 million kilometers apart. From those two positions, nearby stars appear to shift slightly against the background of more distant stars. That shift is incredibly small, far smaller than anything the naked eye could detect. Even for the nearest stars, the angle is measured in fractions of a second of arc, an angle so tiny that if you held a coin thousands of kilometers away it would appear larger. Still, with precise instruments, astronomers can measure that tiny shift. And once they know the angle and the size of Earth's orbit, simple geometry gives the distance to the star. Parallax works beautifully, but it has limits. As stars become more distant, the apparent shift becomes smaller and smaller, until it is too tiny to measure accurately. For centuries, parallax could only be measured for a handful of nearby stars, but modern space telescopes, especially missions like Gaia, have extended this reach dramatically, measuring distances to millions of stars with astonishing precision. Even so, parallax alone cannot map the entire Milky Way. The galaxy is simply too large, so astronomers needed another method, something that could work over greater distances. This is where standard candles come in. A standard candle is an object whose intrinsic brightness is known. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it must be. A nearby candle looks bright, a distant one faint, but if all candles have the same true brightness, the difference in appearance reveals the distance. In astronomy, one of the most important standard candles is the Cepheid variable star. These stars pulsate in a steady rhythm, growing brighter and dimmer over a regular period. Early in the 20th century, astronomers discovered that the length of that period is directly related to the star's true luminosity. A Cepheid that pulsates slowly is intrinsically brighter than one that pulsates quickly. By measuring the period of a Cepheid's pulsation, astronomers can determine its true brightness. Comparing that to its apparent brightness gives the distance. This method allowed astronomers to measure distances far beyond the reach of parallax, extending their map of the Milky Way outward into regions tens of thousands of light years away. It was one of the key tools Harlow Shapley used when he showed that the Sun is not at the centre of the galaxy. But Cepheids are not the only standard candles. There are other types of stars and stellar events that can serve a similar purpose. One example is R-Lyrae stars, which are less luminous than Cepheids but still useful for measuring distances within our galaxy, particularly in globular clusters. Each type of standard candle has its own range and its own uncertainties, but together they allow astronomers to build a more complete picture of the galaxy's structure. There is another method as well, one that relies not on brightness, but on motion. Stars in the Milky Way are not stationary. They orbit the centre of the galaxy, and their motions carry information about their positions and distances. By measuring how stars move across the sky, a quantity called proper motion, and combining that with their radial velocity, their motion toward or away from us, astronomers can infer their trajectories and distances in certain cases. It's a bit like watching boats on a distant ocean. A boat that appears to move quickly across your field of view is probably closer than one that drifts slowly, though other factors must be considered. With careful measurements and models, astronomers can extract distance information from motion itself. Radio astronomy introduced yet another powerful technique. Certain clouds of gas emit radiation at very specific wavelengths, particularly hydrogen gas, which produces a signal at 21 centimeters. By observing this emission and measuring how its frequency is shifted by the Doppler effect, astronomers can determine how fast the gas is moving relative to us. Because the rotation of the Milky Way is fairly well understood, those velocity measurements can be used to estimate distances to gas clouds and star-forming regions. This method helped reveal the spiral structure of the galaxy, showing that we live in a disk with distinct arms rather than a random scattering of stars. Still, even these methods have limitations. Dust obscures visible light, making distant stars appear dimmer than they truly are. Gas clouds can distort measurements. Motions can be influenced by local gravitational effects. Every technique requires careful calibration and cross-checking. And that brings us to one of the quiet revolutions in astronomy, observing the universe in wavelengths beyond visible light. Infrared light in particular is incredibly useful for studying the Milky Way. Dust that blocks visible light often allows infrared to pass through. This means infrared telescopes can see stars and structures hidden behind thick clouds of dust. The James Webb Space Telescope is designed precisely for this purpose. Its instruments are sensitive to infrared wavelengths, allowing it to peer into star-forming regions and through dusty spiral arms with unprecedented clarity. This doesn't just produce beautiful images, it provides better data for measuring distances. By identifying standard candles in regions that were previously obscured, and by mapping star-forming clusters with greater precision, Webb helps refine our three-dimensional map of the galaxy. It's worth pausing for a moment to appreciate how extraordinary this is. The Milky Way is vast beyond everyday comprehension, yet we are gradually learning to measure its structure with increasing accuracy, using nothing more than light collected by instruments orbiting far above Earth. There's also something quietly poetic about the fact that light itself carries the information we need. Every photon arriving at a telescope has travelled across space, sometimes for thousands or tens of thousands of years, bringing with it a tiny piece of the story. By collecting and analysing that light, astronomers reconstruct distances, motions, temperatures, and compositions, turning faint glimmers into maps of enormous regions. And even now the process continues. New surveys, new telescopes, and new techniques are constantly refining the distance scale, reducing uncertainties and filling in gaps. Our map of the Milky Way is not a finished chart, but an evolving one, becoming clearer with each passing year. Understanding distances is more than just an academic exercise. It is the foundation for everything else. To know where we are in the galaxy, to understand the structure of spiral arms, to measure how stars are born and how they move, all of it depends on knowing how far away things are. Without distance, the galaxy would remain a flat painting on the sky, beautiful but shallow. With distance, it becomes a vast three-dimensional landscape filled with depth and motion. If we can measure how far away stars and gas clouds are, what does the large-scale structure of the Milky Way actually look like? And how do spiral arms, dust lanes and star-forming regions combine to shape the neighbourhood where our Sun quietly orbits? Once astronomers began to measure distances with some confidence, a new picture of the Milky Way started to take shape. It was not a random scattering of stars, and it was not a simple, uniform disk. Instead, evidence pointed toward a structure that was organised, patterned and dynamic, something more like a vast rotating system with lanes, clusters, and sweeping features stretching across tens of thousands of light years. Those sweeping features are what we now call spiral arms. If you have ever seen photographs of other galaxies, you've likely noticed this pattern immediately. Many galaxies resemble giant pinwheels or whirlpools, with long curved arms winding outward from a bright central region. Those arms are not solid objects, and they are not fixed like the blades of a fan. They are regions where stars and gas are more densely concentrated, places where new stars are born in large numbers, lighting the arms with clusters of bright young stars. For astronomers studying distant galaxies, spiral arms are easy to see. A telescope captures the entire galaxy at once, revealing the structure clearly. But our situation is different. We are inside the Milky Way, embedded within one of those spiral features surrounded by stars, gas and dust. It is like trying to understand the shape of a forest, while standing among the trees, seeing only trunks and branches in every direction. This is the central difficulty of studying our own galaxy. We do not have an external viewpoint. Early astronomers suspected that the Milky Way might be a spiral galaxy by comparing it with others, but confirming that idea required indirect methods. Observations of star clusters, gas clouds, and radio emissions gradually revealed patterns that suggested curved arms winding around the galactic centre. Over time, the evidence became overwhelming. The Milky Way is indeed a spiral galaxy, and our Sun resides in a smaller feature known as the Orion Spur, a kind of bridge between two larger arms. But even after that realization, another challenge remained, one that made mapping the galaxy far more difficult than mapping most others. Dust. Interstellar dust is one of the quiet but persistent obstacles in astronomy. It is not like the dust in your home, though it shares some similarities. These are tiny particles of carbon, silicates and frozen compounds scattered through space in enormous clouds. Each particle is microscopic, but when billions upon billions of them lie between us and distant stars, they can block or scatter light very effectively. Visible light, the kind our eyes detect, is especially vulnerable to dust. Shorter wavelengths are scattered more easily, which is why distant stars often appear reddened, their blue light filtered out as it passes through dusty regions. This effect can be dramatic. Entire regions of the galaxy are hidden behind thick dust clouds, appearing as dark lanes cutting across the Milky Way's glow. If you have ever looked at photographs of the Milky Way taken from very dark locations, you may have noticed these dark streaks, irregular and branching, like cracks in a luminous surface. Those are not empty spaces. They are dense clouds blocking the light from stars behind them. For early astronomers, dust created a profound illusion. It made the galaxy appear smaller and more uniform than it really is, because distant stars were simply invisible. It also distorted measurements of distance, since stars dimmed by dust could be mistaken for being farther away than they truly were. Imagine trying to estimate the distance of streetlights in a city on a foggy night. Lights farther away appear dimmer, but so do lights hidden behind thicker fog. Without knowing how much fog lies in between, judging distance becomes uncertain. That was the situation astronomers faced when mapping the Milky Way using visible light alone. This is one of the reasons Harlow Shapley's early estimates of the galaxy's size were larger than modern values. Dust made distant objects appear dimmer, leading to overestimated distances. Later observations, especially in radio and infrared wavelengths, helped correct those errors and refine the map. Infrared light turned out to be particularly important. Unlike visible light, infrared can pass through dust much more easily. Regions that appear dark in optical images often glow in infrared, revealing stars and structures hidden behind the dusty veil. This ability to see through dust is one of the reasons the James Webb Space Telescope is so powerful for studying the Milky Way. By observing in infrared wavelengths, Webb can peer into star-forming regions, trace the distribution of gas and young stars, and measure distances in areas that were once obscured. But before space telescopes, astronomers found another way to map the galaxy, one that did not rely on visible light at all. Radio astronomy opened a new window on the Milky Way in the mid-20th century. Neutral hydrogen, the most abundant element in the galaxy, emits radiation at a wavelength of 21 centimeters. This emission can pass through dust almost unhindered, allowing astronomers to detect hydrogen clouds across vast distances. By measuring the Doppler shift of this radiation, astronomers could determine how fast different clouds of gas were moving toward or away from us. Because the rotation of the galaxy follows a predictable pattern, those velocity measurements could be used to estimate distances and positions of gas clouds. When astronomers mapped the distribution of hydrogen using radio observations, a remarkable pattern emerged. The gas was not evenly distributed. It formed long, curved structures consistent with spiral arms. For the first time, the spiral nature of the Milky Way was revealed not through direct imaging, but through careful analysis of radio signals collected by large dishes on Earth. It was a bit like mapping the shape of a coastline by listening to echoes in the dark. Even so, uncertainties remained. Spiral arms are not rigid structures. They are dynamic regions where stars and gas move in complex ways. Stars drift in and out of arms over millions of years, while the arms themselves are patterns shaped by density waves, gravitational influences that compress gas and trigger star formation as they pass. This means the arms are not permanent solid features. They are more like traffic jams in a rotating disk, regions where material temporarily accumulates and then moves on. Understanding this required not only observations but also theoretical work, models of galactic dynamics that explained how spiral patterns could persist over long periods. Meanwhile, astronomers continued refining the map of our local region. By studying the distribution of young stars, star-forming nebulae, and open clusters, they identified the Orion Spur as our home within the galaxy. This spur is not one of the major arms like Sagittarius or Perseus, but it is still a rich and active region, containing many of the bright stars visible in our night sky. If you look up on a clear evening and recognize familiar constellations like Orion, Cygnus, or Scorpius, you are seeing stars that are part of this broader neighborhood, members of the same spiral feature that contains our Sun. There is something quietly grounding about that realization. The night sky is not a random scattering of lights. It is a local landscape, a nearby region within a much larger structure, and the stars you see are, in a sense, your galactic neighbors. But the farther astronomers tried to look, the more the problem of dust returned. The central region of the galaxy, where the spiral arms converge and the density of stars increases dramatically, is almost completely hidden in visible light. Thick clouds of dust obscure the view, making it impossible to see the galactic center directly with ordinary telescopes. It wasn't until radio and infrared observations became more advanced that the true nature of the galactic center began to emerge. Observations revealed a dense cluster of stars and the presence of a supermassive black hole, Sagittarius A star, whose gravitational influence can be traced by watching the rapid orbits of nearby stars. Even today, studying that region is challenging. Dust, crowding, and intense radiation make observations difficult, and every new instrument brings a clearer but still incomplete picture. The same is true for many other parts of the galaxy. Mapping the Milky Way is not like mapping a landscape in daylight. It is more like reconstructing a city from scattered glimpses, partial signals, and measurements taken across enormous distances. And yet, progress continues. The James Webb Space Telescope is now providing images and data that allow astronomers to examine star-forming regions in unprecedented detail. By observing in infrared, Webb can penetrate dusty nebulae, revealing the birthplaces of stars and the structure of molecular clouds. These observations help refine models of spiral arm structure and improve distance measurements to regions that were once hidden. Each new observation adds another piece to the map, another layer of clarity to our understanding of where we are. It is worth pausing to reflect on how remarkable this is. We are inhabitants of a small planet orbiting an ordinary star, located tens of thousands of light years from the center of a galaxy that itself contains hundreds of billions of stars. And yet, through careful observation and patient reasoning, we've begun to chart that galaxy, to understand its structure, and to locate our own position within it. We have learned that the Milky Way is not flat, not uniform, and not fully visible to the eye. It is a layered, dynamic system shaped by gravity, motion, and time, with spiral arms winding through vast clouds of gas and dust. And as our instruments improve, especially with telescopes capable of seeing through those dusty regions, the map becomes sharper, the details clearer, and our sense of place more precise. If we know the general structure of the galaxy and the spiral feature we inhabit, what is our exact address within it, and how precisely can we describe the Sun's position in this immense rotating system of stars? As astronomers struggled to map the Milky Way using visible light, one frustrating reality kept slowing progress. No matter how carefully they measured star positions or brightness, large portions of the galaxy simply refused to reveal themselves. Entire regions appeared dark, not because nothing was there, but because thick clouds of dust blocked the light from reaching Earth. It was like trying to understand the layout of a vast city while looking through layers of fog and smoke. You could see the nearer streets clearly, but distant neighborhoods faded into darkness. And somewhere beyond that haze, structures existed that you could only guess at. For a long time, this limitation seemed unavoidable. Visible light was all astronomers had. But in the early 20th century, a new window into the universe began to open, one that did not depend on light our eyes could see at all. It began with radio waves. Radio waves are a form of electromagnetic radiation, just like visible light, but with much longer wavelengths. Because of those longer wavelengths, radio waves can pass through dust clouds that block visible light. Regions of the galaxy that appear opaque in optical images often become transparent when observed in radio frequencies. This property made radio astronomy one of the most powerful tools ever developed for studying the structure of the Milky Way. The story of radio astronomy's beginnings is an interesting one. In the 1930s, an engineer named Karl Jansky was investigating sources of interference in radio communications. While working with a rotating antenna, he discovered a faint, steady hiss coming from a fixed direction in the sky, the direction of the centre of the Milky Way. Jansky had unintentionally detected radio waves from our galaxy. At first, the discovery attracted little attention outside a small circle of scientists, but over the following decades, astronomers began building larger and more sensitive radio telescopes, dishes capable of detecting faint signals from space. These telescopes did not produce images in the way optical telescopes did. Instead, they measured radio emissions at specific wavelengths, mapping the intensity and distribution of signals across the sky. One of the most important discoveries came from studying neutral hydrogen, the simplest and most abundant element in the universe. Hydrogen atoms can emit radio waves at a wavelength of 21 centimeters, a signal produced when the orientation of the electron spin flips relative to the proton. This transition is rare for any individual atom, but in the vast clouds of hydrogen gas filling the galaxy, it happens often enough to produce a detectable signal. That 21 centimeter line turned out to be extraordinarily useful. Because hydrogen gas is spread throughout the Milky Way, observing this emission allowed astronomers to trace the distribution of gas across enormous distances, even in regions completely hidden by dust in visible light. But there was another crucial advantage. The frequency of the 21 centimeter signal shifts slightly depending on how fast the gas is moving toward or away from us, an effect known as the Doppler shift. By measuring that shift, astronomers could determine the velocity of gas clouds along the line of sight, and since the Milky Way rotates, the velocities of gas clouds depend on their positions within the galaxy. Clouds closer to the galactic centre move at different speeds than those farther out. By combining velocity measurements with models of galactic rotation, astronomers could estimate distances to these clouds. In this way, radio observations transformed the Milky Way from a vague, flattened glow into something with structure and motion. Maps constructed from hydrogen emissions began to reveal long curved concentrations of gas, patterns consistent with spiral arms. These arms could not be seen directly in visible light, but the radio data traced their outlines, showing how they wound around the galactic centre. For the first time, astronomers could begin to piece together a large-scale map of the Milky Way's spiral structure. It was a bit like mapping a coastline by listening to the sound of waves rather than seeing the shore. The results were both exciting and humbling. Our galaxy was larger and more complex than many had imagined. The Sun was not near the centre, and it was not in one of the most massive spiral arms either. Instead, we appeared to reside in a smaller structure, a spur or bridge between larger arms. This region, now known as the Orion Spur, contains many familiar stars and nebulae visible in our night sky. The Orion Nebula, the Eagle Nebula, and numerous other star-forming regions are part of this broader neighbourhood. Radio astronomy also revealed something else important. The Milky Way is not static. Gas clouds move, collide, and collapse to form new stars. Supernova explosions send shock waves through interstellar space, compressing gas and triggering further star formation. The galaxy is a dynamic system, constantly evolving on timescales far longer than a human lifetime. As radio observations improved, astronomers began studying not only hydrogen, but also molecules such as carbon monoxide, which traces dense molecular clouds where stars are born. These observations provided even more detail about the structure of spiral arms and the distribution of star-forming regions. It became clear that spiral arms are not solid structures like the spokes of a wheel. They are regions of higher density, areas where gas and stars are temporarily concentrated as waves of gravitational influence move through the galactic disk. Stars drift in and out of these arms over millions of years. while the pattern of the arms persists. Understanding this required combining observations with theoretical models of galactic dynamics, a reminder that mapping the Milky Way is not just about collecting data, but also about interpreting it. Radio astronomy also played a crucial role in studying the central region of the galaxy. As visible light telescopes struggled to see through the thick dust toward the galactic center, radio observations detected strong emissions from that direction, indicating a dense and active environment. Over time, these studies helped identify the location of Sagittarius A star, the compact radio source at the heart of the Milky Way, now known to be associated with a supermassive black hole. All of this information, gathered through radio waves invisible to the human eye, gradually transformed our understanding of our home galaxy. The Milky Way was no longer just a luminous band across the sky. It was a structured, rotating system with spiral arms, star-forming regions, and a complex distribution of gas and dust. And yet, radio astronomy did not solve every problem. While radio waves can penetrate dust, they do not provide the same level of detail about individual stars as optical or infrared observations. Mapping gas clouds is incredibly useful, but to understand our exact position and the detailed structure of our neighborhood, astronomers needed complementary data, observations in other wavelengths that could reveal stars hidden behind dust, while still providing high resolution. This is where infrared astronomy began to play a larger role, and where modern space telescopes, including the James Webb Space Telescope, have become so important. Infrared observations can reveal stars embedded in dusty regions, measure the properties of star-forming clouds, and refine distance measurements using standard candles that were previously obscured. When combined with radio data tracing gas and optical data measuring stellar motions, a far more complete picture emerges. It is a bit like assembling a layered map, each wavelength revealing a different aspect of the galaxy. Visible light shows bright stars and clusters. Radio waves trace gas and large-scale structure. Infrared penetrates dust and reveals hidden regions. Together, they create a three-dimensional view of the Milky Way. And with each new observation, the map becomes clearer, the spiral arms more precisely defined, the distances more accurately measured. What once appeared as a flat, glowing band has gradually resolved into a vast, intricate system, and our place within it is no longer just an approximation, but an increasingly precise location. After astronomers began to understand the large-scale structure of the Milky Way, and after radio observations revealed the presence of spiral arms winding through the galaxy, a question naturally became more precise. It was no longer enough to say that we live somewhere in the Milky Way. The map was improving, the distances were becoming clearer, and scientists wanted to know something more exact. Where, within this enormous structure, is the Sun actually located? At first glance, the answer sounds simple. The Sun is about 26,000 light-years from the centre of the galaxy. That number appears in textbooks, documentaries, and articles, and it is correct as far as it goes. But it is only part of the story because the Milky Way is not just a disk with a centre and an edge. It has spiral arms, bridges of stars and gas, regions of star formation, and complex patterns of motion. Knowing our distance from the centre is like knowing how far you live from the centre of a city without knowing which neighbourhood you're in. To understand our real address, astronomers had to figure out not just how far away the centre is, but which structure we occupy within the galactic disk. This turned out to be surprisingly difficult. For a long time, the spiral structure of the Milky Way was only partially understood. Radio observations traced the large arms, particularly the Sagittarius arm and the Perseus arm, but the finer details were uncertain. The region around the Sun did not appear to lie neatly inside one of the major arms. Instead, evidence suggested that we were located in a smaller feature, something between the larger structures. That feature is now called the Orion Spur, sometimes also referred to as the Orion Arm, though spur is the more accurate term. A spur, in galactic terms, is a smaller branch or bridge of stars and gas connecting two larger spiral arms. It is not as massive or as densely packed as the main arms, but it is still a significant structure containing star clusters, nebulae, and molecular clouds where new stars are born. Our solar system sits within this spur, embedded in a region of the galaxy that is neither crowded like the inner arms nor sparse like the far outer disk. It is, in a sense, a middle ground. To picture this, it helps to imagine looking at a spiral galaxy from above. You would see several sweeping arms curving outward, with smaller branches and feathers extending from them. Somewhere along one of those smaller branches, about halfway between the centre and the outer edge, you would find a single, unremarkable yellow star. That star is the Sun. More precisely, the Sun lies roughly 26,000 light-years from the galactic centre and about 700 light-years above the midplane of the galaxy, meaning we are not exactly in the densest part of the disk but slightly above it. That vertical offset is small compared to the galaxy's overall thickness, but it is measurable. And we are moving! The Sun orbits the centre of the Milky Way at a speed of about 220 kilometers per second. That is fast enough to travel from Warsaw to Madrid in about 3 seconds. Yet we do not feel this motion at all because everything around us, the planets, the stars in our neighbourhood, even vast clouds of gas, is moving together in roughly the same direction. One complete orbit around the galaxy takes about 230 million years. Astronomers sometimes call this a galactic year. When the dinosaurs were just beginning to appear, the solar system was in a different part of its orbit around the Milky Way. Since then, we have travelled only a small fraction of the way around. Thinking about that can be quietly grounding. Human history, all of it, agriculture, cities, science, recorded language, occupies only a tiny sliver of a single galactic orbit. But returning to our location in the Orion Spur, one of the most interesting aspects of this region is how rich it is in features that are familiar to observers on Earth. Many of the bright nebulae visible in the night sky are part of this same structure. The Orion Nebula, one of the most famous star-forming regions, lies within the spur. So does the Eagle Nebula, home to the famous Pillars of Creation, and the Lagoon Nebula, glowing softly in the constellation Sagittarius. These regions are nurseries of stars, vast clouds of gas collapsing under gravity to form new suns and planetary systems. They are scattered along the spur like lights along a distant shoreline, marking regions where the galaxy is actively renewing itself. The presence of so many star-forming regions nearby is one reason our night sky is so rich. If we lived in a more sparsely populated part of the galaxy, the sky might look very different, darker, with fewer bright stars and nebulae. At the same time, our position is not too close to the most intense star-forming regions, where massive stars live fast and die violently in supernova explosions. Those explosions release enormous amounts of radiation and can disrupt nearby planetary systems. Being somewhat removed from those regions may have contributed to the long-term stability of Earth's environment. There is a concept sometimes discussed by astronomers called the galactic habitable zone. It is not a sharply defined region, but rather an idea that certain parts of a galaxy may be more favourable for life than others. Too close to the centre, and the environment becomes crowded and hazardous, with frequent supernovae and strong gravitational disturbances. Too far out, and there may not be enough heavy elements, the building blocks of planets and life, because those elements are forged in stars and spread through supernova explosions over time. Our position, in a relatively calm region, with a rich supply of heavy elements, but a moderate rate of catastrophic events, may be close to ideal. It is one of those realizations that does not prove anything by itself, but it invites reflection. We are not at the centre of the galaxy, but we are not in an empty void either. We are in a region that seems, at least so far, to be compatible with the development of complex life. Understanding this location has required increasingly precise measurements. One of the challenges is that distances to star-forming regions and clusters must be determined accurately to map the spiral structure properly. parallax measurements from space telescopes, especially missions like Gaia, have provided extraordinarily detailed distance data for millions of stars, allowing astronomers to trace the structure of the Orion spur with much greater confidence. Infrared observations have also been crucial. Dust clouds that obscure visible light become transparent in infrared, revealing clusters and stars that were previously hidden. The James Webb Space Telescope is now extending this work, observing star-forming regions in unprecedented detail and refining distance estimates to key objects within our galactic neighbourhood. These measurements help astronomers determine not only where structures are located, but how they move. Spiral arms are not static. Stars drift in and out of them, and the pattern of the arms itself rotates at a different speed from individual stars. Our solar system has likely passed through different spiral features over the course of its history, though these passages occur over tens of millions of years, far too slowly to notice within a human lifetime. Another detail that adds depth to our address is our motion relative to nearby stars. The Sun is not simply orbiting the galactic centre. It is also moving slightly up and down through the galactic plane in a gentle oscillation that takes tens of millions of years to complete. At present, we are slightly above the plane, moving in a slow cycle that will eventually carry us below it before returning again. This vertical motion is subtle, but it reminds us that the galaxy is not a flat static disk. It is a dynamic system, with stars following complex paths shaped by gravity. When astronomers describe our address in the Milky Way, they sometimes summarize it like this. We are located in the Orion spur, about 26,000 light-years from the galactic centre, roughly halfway between the centre and the outer edge, orbiting at about 220 kilometers per second, slightly above the galactic plane, in a relatively calm region between two major spiral arms. That may sound technical, but there is something quietly remarkable about being able to describe our location at all. A few centuries ago, humanity did not know that the Milky Way was a galaxy. A century ago, we did not know our position within it. Today, we can place ourselves on a map of the galaxy with surprising precision, and that precision is improving. The James Webb Space Telescope, along with other modern observatories, is refining our understanding of star-forming regions, measuring distances with greater accuracy, and revealing structures within the Orion spur that were previously hidden. Each observation sharpens the map, making our address in the galaxy a little clearer. There is something comforting about that process. It reminds us that knowledge grows gradually, through patience and careful observation, each generation adding a little more detail to the picture. If our neighbourhood is just one small part of a galaxy this vast, how large is the Milky Way as a whole, and what does its true scale look like when we try to imagine it from edge to edge? Once you begin to understand where we are in the Milky Way, another realization follows almost automatically. Knowing our address is one thing, but grasping the scale of the place we live in is something else entirely. The numbers involved are so large that they tend to lose meaning unless we slow down and approach them carefully, the way you might let your eyes adjust when stepping into a dark room. Let's start with something familiar. The Earth feels large when you're standing on it. Crossing a city can take an hour. Crossing a country can take a day. Crossing an ocean takes many hours, even in a jet travelling close to the speed of sound. Distances on Earth are meaningful because we experience them directly, with time, motion, and effort. Now consider the distance from Earth to the Moon. Light takes about 1.25 seconds to travel that far. That already feels like a stretch of imagination, but spacecraft have made that journey in a few days, and we have photographs of astronauts standing on that distant surface. The Moon is far, but still within reach of human technology. The Sun is farther away, about 150 million kilometers. Light takes 8 minutes to reach us. When you see sunlight, you are seeing the Sun as it was 8 minutes ago. That's an interesting thought, but still manageable. 8 minutes is a short time in everyday life. But then we move outward to the nearest star beyond the Sun, Proxima Centauri. Its light takes more than 4 years to reach Earth. 4 years is long enough for someone to begin university and graduate, long enough for a child to grow noticeably taller, long enough for entire chapters of life to unfold, and yet Proxima Centauri is one of the closest stars in the galaxy. The Milky Way contains hundreds of billions of stars scattered across a disk so large that light takes about 100,000 years to travel from one side to the other. That means if a beam of light began its journey across the galaxy when early humans were first learning to use tools, it still would not have reached the opposite edge today. Trying to picture that distance directly is difficult, so astronomers often rely on comparisons. Imagine shrinking the solar system so that the orbit of Earth around the Sun is the size of a coin. On that scale, the nearest star would be thousands of kilometers away, and the Milky Way would stretch across an entire continent. Or imagine the galaxy as a vast city at night seen from high above. Each star is a light in a window, each cluster a brightly lit neighborhood, each spiral arm a glowing avenue curving through the darkness. Now imagine that city stretching farther than the eye can see in every direction, and that you're standing in one small district, looking out from a single window. That is closer to the truth. The disk of the Milky Way is about 100,000 light-years in diameter, but it is much thinner than it is wide. In most regions, the thickness of the stellar disk is only about 1,000 light-years. That gives the galaxy a shape somewhat like a vast flattened pancake, though even that analogy is imperfect because the central region bulges outward, forming a dense, rounded core. At the very centre lies a supermassive black hole, Sagittarius A star, surrounded by millions of stars packed closely together. But we are far from that crowded region, orbiting in the quieter outer disk. The Sun's distance from the centre, about 26,000 light-years, places us a little more than halfway out. If the galaxy were a large circular park, the Sun would be somewhere in the outer walking paths, rather than near the busy central plaza or the distant fence at the edge. But even the outer disk is enormous. The nearest spiral arm beyond our own lies thousands of light-years away. The bright stars you see in the night sky, the familiar constellations, all belong to a tiny local neighborhood only a few thousand light-year across. Compared to the full diameter of the galaxy, that region is very small. It's a bit like living in one neighborhood of a vast city and seeing only the nearest streets, while distant districts remain invisible beyond the horizon. There is another layer to this sense of scale, and it has to do with time. The Sun, like every other star in the disk, orbits the center of the Milky Way. The speed of this motion is about 220 kilometers per second, fast enough to circle the Earth in less than 3 minutes. Yet the orbit is so large that completing one full revolution takes about 230 million years. Astronomers sometimes call this a galactic year. To put that in perspective, the last time the solar system was in this exact position in its orbit, the continents on Earth were arranged differently. Dinosaurs were beginning to dominate the land and flowering plants had not yet appeared. Entire eras of geological and biological change fit into a single circuit of the galaxy. And since the Sun formed about 4.6 billion years ago, it has completed only about 20 galactic orbits in its entire lifetime. That realization carries a certain quiet weight. The history of humanity, all of recorded civilization, is only a tiny fraction of a single galactic year. There is also the matter of vertical motion. The Sun does not travel in a perfectly flat circle. It moves gently up and down through the galactic plane, oscillating over tens of millions of years. At present, we are slightly above the plane, drifting in a slow cycle that will eventually carry us below it and back again. These motions are so gradual that they are impossible to feel directly, but they are measurable through careful observation of stellar velocities and positions. And yet, despite all this motion and scale, the galaxy does not feel large when you look at the night sky. It feels intimate, even quiet. The stars appear close, the constellations familiar, the Milky Way a soft band of light. That is one of the curious things about the universe. Its true scale is hidden behind distance and perspective, revealed only through measurement and imagination. Modern astronomy has provided increasingly detailed maps of the Milky Way. Surveys of stars, gas and dust have revealed spiral arms, star-forming regions, and vast molecular clouds stretching across hundreds of light years. Space telescopes have measured distances with unprecedented precision, refining our understanding of the galaxy's size and structure. The James Webb Space Telescope is contributing to this work by observing star-forming regions and clusters in infrared light, penetrating dust clouds that once hid large portions of the galaxy. These observations help astronomers refine distance measurements and trace the distribution of stars and gas more accurately than before. Each improvement adds clarity, like adjusting the focus of a lens. There is something quietly remarkable about the fact that we can measure the size of a galaxy at all. We are small creatures on a small planet, yet we have learned to measure distances so vast that light itself takes tens of thousands of years to cross them. And even the Milky Way, immense as it is not unique. When we look beyond it, we see countless other galaxies, many larger, some smaller, scattered across the observable universe. The Milky Way is one among billions, but tonight it is enough to focus on our own galaxy, to let the idea of its size settle gently in the mind. A disk 100,000 light-years wide, hundreds of billions of stars, spiral arms winding slowly through space, a quiet yellow star orbiting in the Orion Spur, carrying a small blue planet and its listeners through the darkness at extraordinary speed, unnoticed and unfelt. Sometimes, understanding scale is not about memorizing numbers, but about letting the realization unfold gradually, like watching the sky darken after sunset. At first, only a few stars appear, then more and more, until the full depth of the night reveals itself. In much the same way, the scale of the Milky Way becomes clearer the longer you sit with it, the longer you allow your imagination to stretch beyond familiar distances. And once you begin to grasp how vast our galaxy truly is, another thought naturally arises. If the Milky Way is so large, and if we are embedded deep within it, why is it actually harder to map our own galaxy than it is to map distant galaxies far beyond it? It might seem like a strange paradox at first. The Milky Way is our home galaxy. We are surrounded by its stars, immersed in its spiral arms, closer to its structure than to any other galaxy in the universe. So you might expect that it would be the easiest galaxy of all to study and map. And yet, the opposite is true. In many ways, it is easier for astronomers to map galaxies millions of light years away than to map the one we live inside. The reason comes down to perspective, distance, and a few quiet but stubborn obstacles that have shaped astronomy for more than a century. To understand this, it helps to imagine something familiar. Picture yourself standing in the middle of a large forest. Trees stretch in every direction. You can see nearby trunks clearly, and perhaps a small clearing here or there, but the overall shape of the forest is difficult to grasp. You cannot see its edges, its curves, or how far it extends beyond the hills. From inside, everything looks like trees and shadows. Now imagine rising high above that forest in a balloon. Suddenly the structure becomes clear. You see the winding river, the dense patches of trees, the open meadows, the boundaries where the forest meets fields. The shape that was impossible to perceive from within becomes obvious from above. That is the difference between mapping the Milky Way and mapping other galaxies. When astronomers observe distant galaxies, they are seeing them from the outside. Even though those galaxies are unimaginably far away, telescopes can capture their entire shape in a single image. Spiral arms, central bulges, dust lanes, all of it becomes visible at once. It may lack fine detail, but the overall structure is clear. With the Milky Way, we do not have that luxury. We are inside the disk, surrounded by stars and gas, with our view blocked in many directions by dust clouds. We cannot step outside and take a picture. That alone would make mapping difficult, but there are other challenges as well. One of the most significant is interstellar dust, which you've encountered before in this journey. Dust absorbs and scatters visible light, hiding distant stars and distorting measurements of brightness and distance. entire regions of the galaxy are obscured in optical wavelengths, especially toward the centre, where dust clouds are thickest. Imagine trying to map a city at night while heavy fog drifts through the streets. Some neighbourhoods remain visible, while others vanish completely, not because they are empty, but because the fog blocks the view. You might mistake those hidden areas for gaps, or misjudge how far away certain landmarks are. Astronomers faced exactly this problem for decades. Early maps of the Milky Way underestimated its size and misrepresented its structure because dust made distant stars invisible. Infrared and radio observations have helped overcome this obstacle. But even with modern instruments, dust still complicates measurements and interpretations. Another difficulty is distance. Stars in the Milky Way lie at vastly different distances from us, from a few light years to tens of thousands of light years away. Determining those distances accurately requires careful measurement using parallax, standard candles or other methods, each with its own uncertainties. When observing a distant galaxy, astronomers do not need to know the distance to every individual star. The galaxy appears as a coherent object, and its overall structure can be studied without resolving every component. But in the Milky Way, the structure must be reconstructed star by star, cloud by cloud, region by region. It is a bit like assembling a puzzle without ever seeing the picture on the box. There is also the challenge of motion. Stars in the Milky Way are not stationary. They orbit the galactic centre, move relative to one another, and sometimes travel in streams or clusters shaped by past gravitational interactions. Gas clouds drift, collide, and collapse. Spiral arms themselves are not rigid structures but patterns that shift over time. This means the galaxy is not a static object that can be mapped once and for all. It is a dynamic system, constantly evolving. When astronomers map distant galaxies, they are usually capturing a snapshot, a moment in time frozen in an image, but when mapping the Milky Way, they are trying to reconstruct a three-dimensional moving structure from incomplete and changing information. There is another subtle complication as well. The brightness of stars varies enormously. Some stars are faint red dwarfs, barely visible even at relatively close distances. Others are brilliant blue giants, visible across vast stretches of the galaxy. When you look at a dense star field, it is not immediately obvious which stars are nearby and which are distant but luminous. Without accurate distance measurements, the sky can be misleading. A bright star might seem close but be far away. A faint star might seem distant but be nearby. Separating those layers requires careful analysis of colour, brightness, and motion, and then there is time itself. Light from different parts of the galaxy takes different amounts of time to reach us. When we observe a star 10,000 light-years away, we are seeing it as it was 10,000 years ago. When we observe a region near the galactic centre, we are seeing events that happened long before recorded history on Earth. This means that a map of the Milky Way is also a map of the past, assembled from light that left its sources at different times. In most cases, the changes over those timescales are small enough that the map remains accurate, but it is still a reminder that we are reconstructing a structure not as it exists now, but as it existed across a range of times. Despite all these challenges, astronomers have made remarkable progress. Radio observations revealed the large-scale distribution of hydrogen gas, tracing spiral arms invisible in optical light. Infrared telescopes penetrated dust clouds, revealing star-forming regions and clusters hidden from view. Space missions like Gaia measured the positions and motions of more than 1 billion stars, providing an unprecedented three-dimensional map of our local region of the galaxy. And now the James Webb Space Telescope is adding another layer of detail, observing star-forming regions, young clusters, and dusty environments with extraordinary sensitivity. Webb does not map the entire galaxy at once, but its observations refine key pieces of the puzzle, improving distance measurements and revealing structures that were previously hidden. Each new dataset adds clarity, reducing uncertainties and filling in gaps, like gradually sharpening the focus of a blurred image. It It is worth pausing to appreciate how extraordinary this process is. Humanity has learned to map a galaxy from the inside, using nothing more than faint light, careful measurement, and patient reasoning. It is a slow, meticulous endeavour, but one that has transformed our understanding of where we are. And yet, the map is still incomplete. There are regions we have not yet studied in detail, structures we do not fully understand, and questions that remain open. That is part of what makes astronomy so compelling. The sky is not a finished book. It is a story still being written, with each new telescope adding another page. For centuries, every improvement in our understanding of the Milky Way followed the same quiet pattern. A new instrument appeared, a little more sensitive, a little more precise, and suddenly parts of the galaxy that had once been hidden began to reveal themselves. First came better optical telescopes, then radio observatories, then infrared detectors lifted above the atmosphere. Each step opened another window, but every window still had limits. Dust clouds continued to block vast regions of space. Many of the most interesting places in the galaxy, star-forming nurseries, dense molecular clouds, and the crowded regions toward the galactic centre, remained difficult to study in detail. Even the most powerful ground-based telescopes had to contend with Earth's atmosphere, which absorbs large portions of infrared light and blurs images with subtle turbulence. Astronomers knew that to see deeper into the Milky Way, they needed a new kind of observatory, one that could operate far above the atmosphere, one that could detect faint infrared light with extraordinary sensitivity, and one that could remain cold enough to prevent its own heat from interfering with the delicate signals it was trying to measure. That observatory became the James Webb Space Telescope. The story of Webb's creation spans decades, involving thousands of engineers, scientists, and technicians across multiple countries. It was designed not simply as a successor to earlier space telescopes, but as something fundamentally different, a telescope built to see the universe in wavelengths that reveal structures hidden from ordinary sight. Unlike the Hubble Space Telescope, which observes primarily invisible and ultraviolet light, Webb is optimized for infrared. This difference is not just technical, it changes what the telescope can see. Infrared light has longer wavelengths than visible light, and those longer wavelengths can pass through clouds of dust that block shorter wavelengths. Regions that appear dark and opaque in visible images often glow in infrared, revealing stars embedded deep within gas clouds, stars that are still forming, stars that have never been seen before. In a sense, infrared vision allows astronomers to look through the walls of the galaxy. This capability is especially important for studying the Milky Way, because so much of our galaxy is veiled by dust. The spiral arms, the star-forming regions, and even the central bulge are threaded with thick clouds that obscure visible light. Webb's infrared instruments can penetrate those clouds, allowing astronomers to observe structures that were once hidden. But Webb's power does not come only from the wavelengths it observes. Its mirror, made of 18 hexagonal segments coated in gold, spans more than 6 meters in diameter, far larger than the mirror of Hubble. That large mirror collects more light, allowing Webb to detect extremely faint objects and resolve fine details in distant regions of space. The gold coating may sound decorative, but it serves a precise purpose. Gold reflects infrared light very efficiently, making it ideal for Webb's instruments. The telescope also operates at extraordinarily low temperatures. To detect faint infrared signals, Webb must remain extremely cold, because heat itself produces infrared radiation. If the telescope were warm, its own glow would overwhelm the signals it's trying to measure. To achieve this, Webb carries a multi-layer sunshield the size of a tennis court, made of thin reflective membranes that block heat from the sun, Earth, and Moon. On the shaded side of that shield, the telescope cools to temperatures around -230 degrees Celsius, cold enough for its instruments to function with remarkable sensitivity. There is something quietly elegant about this design. Webb does not rely on heavy refrigeration systems or complex machinery to stay cold. Instead, it uses geometry, distance, and the steady shadow of its sunshield, a passive approach that allows it to remain stable and efficient. Webb orbits the Sun near a point called Lagrange Point 2, or L2, about 1.5 million kilometers from Earth. From that location, the telescope can keep its sunshield permanently facing the Sun, Earth and Moon, while the instruments point outward into deep space. L2 is not a place you can see from Earth, but it's a region where gravitational forces and orbital motion balance in such a way that a spacecraft can remain in a stable configuration relative to Earth and the Sun. It is a quiet, distant vantage point, ideal for observing the universe. From there, Webb has begun delivering images and data of extraordinary clarity. Some of the most famous early images show distant galaxies and star-forming regions, but Webb's importance for understanding our own galaxy is just as profound. By observing in infrared, it can peer into dense molecular clouds where stars are being born, revealing structures and processes that were previously hidden. These observations help astronomers refine models of star formation, measure distances to clusters embedded in dust, and trace the structure of spiral features with greater precision. For example, regions like the Carina Nebula, the Eagle Nebula, and other stellar nurseries have been observed in unprecedented detail. What once appeared as dark, opaque shapes in visible light are now seen as intricate landscapes of gas and dust, filled with newborn stars and glowing filaments. Each of these regions is part of the larger structure of the Milky Way, and each new observation helps refine our understanding of where these structures lie in three-dimensional space. Webb is also capable of studying the chemical composition of gas clouds and young stars, measuring the presence of molecules such as water, carbon dioxide, and complex organic compounds. These measurements provide clues about the environments in which stars and planets form, and about the processes shaping our galactic neighbourhood. There is another way in which Webb contributes to mapping the Milky Way, and it has to do with precision. Accurate distance measurements depend on identifying standard candles, such as certain types of variable stars, and observing them clearly. In dusty regions where visible light is blocked, these stars can be difficult or impossible to detect with optical telescopes. Webb's infrared sensitivity allows astronomers to identify and study such stars in previously obscured regions, improving the calibration of distance measurements. When distances become more accurate, maps become more accurate. The positions of spiral arms, the sizes of star-forming regions, and the distribution of clusters all become clearer. This is not the kind of discovery that usually makes headlines, because it happens gradually, through careful analysis and refinement, but it is essential. Science often advances not in dramatic leaps, but in steady improvements in clarity, each observation sharpening the picture a little more. There is something deeply human in that process. The patience, the persistence, the willingness to spend years improving a measurement by a small fraction, knowing that each improvement brings us closer to understanding the structure of our home galaxy. Another remarkable aspect of Webb is its ability to study very faint, very distant objects at the same time as nearby regions. While mapping star-forming clouds in the Milky Way, it is also observing galaxies whose light has travelled for billions of years. The same instruments that reveal the birth of stars in our neighbourhood also capture the earliest galaxies in the universe. It is a reminder that our galaxy is part of a much larger cosmic story, and that understanding our place within it is only one piece of a vast and unfolding picture. Still, there is something especially meaningful about using Webb to study the Milky Way itself. For generations, astronomers looked outward to distant galaxies to understand spiral structure, because it was easier to see their shapes from afar. Now, with Webb and other modern instruments, we are beginning to see our own galaxy with similar clarity, not from outside, but from within. We are learning how spiral arms connect, how star-forming regions are distributed, and how our local neighbourhood fits into the larger structure of the disk. And perhaps most strikingly, we are beginning to see the galaxy not as a flat band in the sky, but as a living system filled with motion, change, and ongoing creation. Stars are forming right now in cold clouds of gas. Clusters are emerging from their dusty cocoons. Shock waves from ancient supernovae are compressing new regions of gas, triggering the next generation of stars. The Milky Way is not a static structure. It is active, evolving, and full of processes unfolding on timescales far longer than a human lifetime. Webb allows us to watch some of those processes more clearly than ever before. It is easy to think of telescopes as tools that simply take pictures, but in reality they are instruments of measurement, precision machines designed to extract information from faint signals. Every observation Webb makes adds to a growing archive of data that astronomers around the world analyze, compare, and interpret. From that data, new maps are drawn, new distances calculated, new models refined. And slowly, the question that began this journey, where are we in the Milky Way, is being answered with increasing detail and confidence. We're not at the centre. We're not at the edge. We're in a spur between two spiral arms, orbiting quietly around a distant core, surrounded by regions of star formation and vast clouds of gas and dust. Webb is helping us see that neighbourhood more clearly than ever before. When a new telescope begins operating, astronomers often say that it is like opening a new sense, not just seeing farther, but seeing differently. Every instrument throughout history has revealed something the previous generation could not detect, and each time the universe has turned out to be richer and more intricate than expected. The James Webb Space Telescope is one of those turning points, not because it simply produces sharper images, but because it allows us to observe parts of the Milky Way that were effectively invisible before. To understand why that matters, it helps to think about how limited our vision used to be. Most of the images of space people grew up seeing were taken in visible light, the same range of wavelengths our eyes detect. Visible light telescopes, whether on the ground or in orbit, can show stars, clusters, and glowing gas clouds in extraordinary detail. But visible light is only a narrow slice of the electromagnetic spectrum, and in the Milky Way it is often the slice most easily blocked. Dust grains drifting between the stars are extremely effective at scattering visible light. Entire regions of the galaxy are hidden behind them, not because there is nothing there, but because the light cannot pass through. In photographs taken in visible wavelengths, these regions appear as dark voids, jagged patches that seem empty. But those voids are not empty. They are some of the most active and interesting places in the galaxy. Inside those cold, dark clouds, stars are forming. A star begins its life deep within a dense knot of gas and dust, where gravity slowly pulls material together. At first, the forming star is completely hidden from view. Light from its growing core cannot escape the surrounding cloud. To a visible light telescope, nothing is there, only darkness. Infrared light changes that. Infrared wavelengths are longer than visible light, and they pass through dust far more easily. Where visible light is scattered and absorbed, infrared can slip between the grains, carrying information outward. Webb is designed to detect that infrared glow with extraordinary sensitivity. This means Webb can see stars that are still forming, stars still wrapped in their dusty birth clouds, stars that no optical telescope could reveal clearly. And when Webb looks at a region that once appeared dark, the transformation can be astonishing. What seemed like empty space becomes crowded with structure, filaments of gas, clusters of newborn stars, and intricate patterns shaped by gravity, radiation, and motion. It is a bit like turning on a lantern in a room you thought was empty, and discovering it is full of furniture, walls, and objects you simply could not see before. One of the most remarkable things Webb reveals is the earlier stages of star formation. Before a star ignites, the collapsing gas around it forms a dense core, gradually heating as gravity compresses it. Jets of material may begin to stream outward along the forming star's poles, carving narrow channels through the surrounding cloud. These processes were once understood mostly through theory and indirect observation. Now they can be observed directly in many cases, with details sharp enough to study the shapes of outflows, the structure of disks, and the distribution of gas in ways that were not possible before. Webb also sees protoplanetary disks with unprecedented clarity. Around many young stars, disks of gas and dust form, the raw material from which planets eventually emerge. These disks are often hidden in dusty regions, and even when visible, their fine structures were difficult to resolve. With Webb, astronomers can detect gaps, rings, and asymmetries in these disks, clues that planets may already be forming, sweeping paths through the material as they grow. Observing these disks helps scientists understand how planetary systems develop, including systems that may resemble our own in its earlier stages. There is something quietly powerful about realizing that telescopes like Webb are not only showing us where we are in the galaxy, but also how places like our solar system may have begun. Another capability that sets Webb apart is spectroscopy, the ability to analyze the light from objects and determine their chemical composition. Every element and molecule absorbs and emits light at specific wavelengths, leaving a kind of fingerprint in the spectrum. By studying those spectral fingerprints, astronomers can identify water vapor, carbon monoxide, methane, carbon dioxide, and more complex molecules in star-forming regions and planetary disks. They can measure temperatures, densities, and motions within clouds of gas thousands of light-years away. Earlier telescopes could perform spectroscopy as well, but Webb's sensitivity in the infrared allows it to detect molecules and environments that were previously beyond reach. This matters for understanding our place in the Milky Way, because the distribution of gas and dust, the rate of star formation, and the chemical composition of different regions all help define the structure and evolution of the galaxy. Mapping these properties with greater precision allows astronomers to refine models of spiral arms, star-forming complexes, and the broader galactic environment. Webb also provides extraordinary resolution, meaning it can distinguish fine details in crowded regions. In dense star clusters where thousands of stars lie close together, earlier telescopes often struggled to separate individual sources. Light from neighbouring stars blended, making measurements less precise. With its large mirror and advanced instruments, Webb can resolve many of those crowded fields, separating stars that once appeared merged. That improved resolution allows for more accurate distance measurements, better estimates of stellar populations, and a clearer understanding of how clusters evolve over time. Distance, as you've seen, is the foundation of mapping the galaxy. Every improvement in distance measurement sharpens the map, reducing uncertainties and revealing structures more clearly. Another way Webb sees differently is in its ability to detect extremely faint objects. Some of the stars in our galaxy are small, cool, and dim, emitting most of their energy in infrared wavelengths. These stars are abundant but often difficult to observe in visible light. By detecting these faint infrared sources, Webb helps astronomers build a more complete census of stars in certain regions, improving estimates of stellar density and distribution. Knowing how many stars exist in different parts of the galaxy is essential for understanding its structure and evolution. Webb also observes dust itself, not just the stars behind it. Dust grains emit infrared radiation when warmed by nearby stars, creating a faint glow that reveals the shapes and densities of molecular clouds. Mapping that glow helps astronomers trace the raw material from which new stars will form in the future. In this way, Webb is not only showing us where stars are, but where stars will be. There is another subtle but important advantage to Webb's position in space. Because it orbits far from Earth at the Lagrange point L2, it operates in a very stable thermal and radiation environment. This stability allows for long, uninterrupted observations, sometimes lasting many hours, collecting faint signals that would be difficult to detect in shorter exposures. Long observations are especially valuable when studying distant or faint structures in the Milky Way, where the signals are weak and require time to accumulate. It is worth reflecting for a moment on what all of this means in a broader sense. For most of human history, the Milky Way was simply a luminous band in the sky. Beautiful, but mysterious. Even after telescopes revealed its stellar nature, large portions remained hidden behind dust, inaccessible to observation. Now, with instruments like Webb, those hidden regions are becoming visible. We're beginning to see the galaxy not just as it appears from Earth, but as it truly is, a complex, layered system filled with motion, formation, and change. And yet, Webb does not work alone. Its observations are combined with data from other missions, such as Gaia, which measures the positions and motions of stars with extraordinary precision, and radio observatories that map gas clouds across vast distances. Together, these datasets form a kind of three-dimensional atlas of the Milky Way, each wavelength adding a different layer of information. Visible light shows bright stars and clusters. Radio waves trace hydrogen gas and spiral structure. Infrared reveals hidden stars and molecular clouds. Motion measurements show how everything moves through space. When all of these layers are combined, the map becomes far richer than any single instrument could provide. It is a gradual process, one that unfolds over years and decades. But each observation adds clarity, like slowly adjusting the focus of a lens until the image becomes sharp. One of the most striking aspects of Webb's observations is how they change our perception of familiar regions. Nebulae that once appeared as soft, hazy patches now reveal intricate networks of filaments, knots, and glowing arcs shaped by stellar winds and radiation. Star clusters once seen as simple groupings now show layers of stars at different stages of evolution. These details are not just visually striking, they provide data that help astronomers understand how stars form, how clusters evolve, and how spiral arms are structured. And as these observations accumulate, they are beginning to refine our understanding of our own galactic neighbourhood, the Orion Spur, revealing how star formation is distributed, how molecular clouds are arranged, and how our region fits into the broader architecture of the Milky Way. There is something quietly remarkable about realizing that a telescope orbiting far beyond Earth is helping us understand not only distant galaxies, but also the region of space in which our own sun was born billions of years ago. The same instruments that study the earliest galaxies in the universe are also revealing the birthplaces of stars in our own galaxy today. Long before telescopes like James Webb existed, astronomers already knew that stars were still being born in the Milky Way. The evidence was visible even through modest instruments, glowing nebulae, dark clouds, and clusters of young blue stars scattered along the band of the galaxy. These regions were recognized as stellar nurseries, places where gravity slowly gathers gas and dust until new stars ignite. But knowing that star formation happens is very different from seeing it clearly. For decades, many of these regions were partly hidden behind curtains of dust, and the earlier stages of starbirth were especially difficult to observe. Astronomers could detect hints, infrared emissions, radio signals, spectral fingerprints of molecules, but the detailed structures, the shapes of collapsing clouds, the jets from newborn stars, and the interactions between radiation and gas often remained indistinct. That has begun to change. With the James Webb Space Telescope observing in infrared wavelengths, astronomers are now able to look into nearby star-forming regions with a level of detail that was simply not possible before. And what they are finding is not just visually striking, but scientifically important, because it is refining our understanding of how active our local region of the Milky Way really is. One of the most significant realizations is that star formation is not evenly distributed. It tends to occur in clusters and complexes, vast molecular clouds spanning tens or even hundreds of light years, where gravity, turbulence, magnetic fields, and radiation all interact in complex ways. Some of these regions are relatively close to us in galactic terms, only a few thousand light-years away, part of the same spiral feature that contains our Sun. Observing them in detail provides insight not only into how stars form today, but also into how our own solar system may have formed billions of years ago in a similar environment. Webb has revealed that these molecular clouds are far more structured than previously thought. Instead of smooth, uniform shapes, they are intricate networks of filaments, knots, and dense cores, shaped by shock waves, stellar winds, and gravitational collapse. Within these filaments, clumps of gas begin to condense, gradually forming protostars. These protostars are often completely invisible in visible light, still wrapped in thick cocoons of dust, but in infrared they glow softly, their heat radiating outward through the surrounding material. Webb's sensitivity allows astronomers to detect these faint objects and study their properties, measuring temperatures, masses, and the composition of the gas around them. Another discovery involves the role of feedback, the influence that young stars have on their environment. Massive stars emit intense ultraviolet radiation and powerful stellar winds, which can compress nearby gas clouds, triggering new waves of star formation or disperse gas, halting star formation in certain regions. Webb's observations have shown these processes in remarkable detail. In some nebulae, pillars of gas are sculpted by radiation from nearby massive stars, their surfaces glowing while their interiors remain cold and dense. Within those pillars, new stars may be forming, shielded from the intense radiation outside. These structures are not static. Over time, radiation erodes them, gradually dispersing the gas. Star formation is therefore a race against time, gravity trying to gather material while radiation and winds try to disperse it. Understanding this balance helps astronomers explain why some molecular clouds produce many stars while others produce few. Webb has also provided new insight into protoplanetary disks, the rotating disks of gas and dust around young stars where planets begin to form. These disks are common in star-forming regions, but observing their detailed structure has often been difficult, especially when they are embedded in dusty environments. With its infrared capabilities, Webb can detect the thermal glow of dust within these disks, revealing gaps, rings, and other features that may indicate the presence of forming planets. Observations like these are helping scientists understand how planetary systems develop, how quickly planets can form, and how common such systems might be. This research is not just about distant stars. It connects directly to our own history, because the Sun likely formed in a similar molecular cloud, surrounded by other young stars, embedded in gas and dust that eventually dispersed, leaving behind the solar system we know today. There is something quietly profound in that connection. When Webb observes a young star surrounded by a disk of dust, it may be witnessing a process that once shaped the environment in which Earth itself formed. Another area where Webb is contributing is in measuring the chemical composition of star-forming regions. By analysing infrared spectra, astronomers can detect molecules such as water, methane, carbon dioxide, and complex organic compounds within molecular clouds and disks. These molecules are important not only for understanding star formation, but also for understanding the potential for life elsewhere in the galaxy. The chemical ingredients for life appear to be widespread, forming in the cold depths of interstellar space long before planets exist. In this way, star formation is not just the birth of stars, but the beginning of planetary systems and potentially the conditions necessary for life. Closer to home, Webb's observations are refining distance measurements to nearby star-forming regions. Accurate distances are essential for mapping the structure of the Orion spur and understanding how different clouds and clusters are arranged in three-dimensional space. Some regions, once thought to be part of a single structure, have turned out to be separate clouds at different distances, while others previously believed to be unrelated have been shown to belong to the same complex. These refinements may seem small, but they gradually improve our map of the galaxy and our understanding of where we are within it. Another discovery involves the distribution of small, faint stars. Many of the stars forming in molecular clouds are low-mass red dwarfs, dim objects that emit most of their light in infrared wavelengths. These stars are extremely numerous but often difficult to detect with visible light telescopes. Webb's sensitivity allows astronomers to detect these faint stars in large numbers, improving estimates of how many stars form in different regions and how the stellar population evolves over time. This matters because the mass distribution of stars, how many large stars form compared to small ones, affects everything from the chemical evolution of the galaxy to the rate of supernova explosions and the enrichment of interstellar gas. There is also growing evidence, supported by Webb's observations, that star formation in our local region of the galaxy may occur in bursts rather than at a steady uniform rate. Molecular clouds can remain relatively quiet for long periods, then suddenly begin forming stars rapidly when conditions change, perhaps triggered by shock waves from nearby supernovae or collisions between clouds. This dynamic behavior helps explain why some regions appear crowded with young stars while others are relatively quiet. All of these discoveries contribute to a more detailed picture of our galactic neighbourhood. The Orion Spur is not just a bridge between spiral arms. It is an active environment filled with molecular clouds, clusters, and ongoing star formation. And yet, despite this activity, our immediate surroundings remain relatively calm. The nearest massive star-forming regions are far enough away that their intense radiation and supernova explosions pose little threat to the stability of the solar system. It is a delicate balance, enough activity to enrich the interstellar medium with heavy elements, but not so much as to make the environment hazardous for life. There is something quietly reassuring in that balance, a reminder that our place in the galaxy is not only measurable, but also, in some ways, fortunate. As Webb continues to observe star-forming regions, astronomers are beginning to refine the larger map of the Milky Way, improving our understanding of how spiral arms connect, how gas flows through the disk, and how our local region fits into the broader structure of the galaxy. Each new observation adds another piece to the puzzle, bringing the map into sharper focus. And as that map becomes clearer, another realization begins to emerge. The Milky Way is not a static backdrop but a dynamic system, slowly evolving, with stars orbiting, gas clouds shifting, and spiral patterns changing over time. For a long time, when astronomers described our place in the Milky Way, the answer sounded reasonably precise, but it was still built on a map that contained many blurred edges. We knew we were about halfway out from the galactic centre. We knew we were in a smaller structure between two major spiral arms. We even had a name for it, the Orion Spur. But many of the details remained uncertain. The exact boundaries of that spur, the positions of star-forming regions within it, the distances to clusters embedded in dust, and even the shapes of nearby molecular clouds were still being refined. A map, after all, is only as accurate as the measurements used to draw it. And until recently, many of those measurements were limited by what we could see. The James Webb Space Telescope is not redrawing the entire map of the Milky Way overnight, but it is sharpening it, clarifying distances, revealing structures that were previously hidden, and refining our understanding of the region around us in ways that are subtle but important. One of the key ways Webb is doing this is by improving distance measurements to objects embedded in dusty regions. Earlier telescopes, especially those working in visible light, often struggled to observe stars deeply embedded in molecular clouds. These stars were either invisible or appeared dimmer than they truly were, making distance estimates uncertain. Webb's infrared sensitivity allows astronomers to detect these stars clearly, measure their brightness more accurately, and identify standard candles in regions that were previously inaccessible. With better distance measurements, the positions of star clusters and nebulae can be placed more precisely in three-dimensional space. This might sound like a small adjustment, but when multiplied across dozens or hundreds of regions, it gradually transforms the map. Spiral features that once appeared vague become better defined. Structures that seemed connected may turn out to lie at different distances, while others previously thought unrelated are revealed to be part of the same system. It is a bit like cleaning a fogged window. The scene outside does not change, but the details become clearer and relationships between objects become easier to see. Another area where Webb is refining the map involves star-forming regions. These regions are often used as markers of spiral structure because new stars tend to form along the arms where gas is compressed. By studying these regions in detail, astronomers can trace the shape of spiral features and determine how they connect. Webb's observations reveal the internal structure of these clouds, showing where dense cores are located, where young stars are emerging, and how gas is distributed. This information helps astronomers understand not only where these regions are, but how they evolve and how they relate to the larger galactic environment. In some cases, Webb has revealed that certain star-forming complexes are more extended than previously thought, stretching across larger regions of space. In others, it has identified clusters of young stars that were completely hidden in visible light, adding new points to the map. Each of these discoveries may seem small on its own, but together they improve our understanding of the Orion Spur and the nearby spiral arms. There is also the matter of stellar populations. The Milky Way contains stars of many different ages, from newly formed protostars to ancient stars that formed billions of years ago. By studying the distribution of these populations, astronomers can learn about the history of star formation in different regions. Webb's ability to detect faint, cool stars and brown dwarfs in dusty environments is helping astronomers build a more complete census of stars in certain regions. Knowing how many stars of different masses exist in a region helps refine models of how that region formed and evolved. This in turn contributes to a more accurate picture of our galactic neighbourhood. Another important contribution comes from Webb's spectroscopy. Its ability to analyse the light from stars and gas to determine chemical composition and physical conditions. By studying the chemical makeup of molecular clouds and young stars, astronomers can trace the enrichment of heavy elements and the processes that distribute those elements through the galaxy. These chemical fingerprints provide clues about the history of star formation and the flow of material through the spiral arms. Regions with similar chemical signatures may have formed from the same reservoir of gas or experienced similar evolutionary histories. Mapping these patterns helps refine our understanding of how different parts of the galaxy are connected. Webb is also helping to clarify the structure of nearby molecular clouds, some of which are closer to the solar system than previously thought. These clouds, though relatively small on a galactic scale, play an important role in shaping the local interstellar environment. For example, the Sun currently resides within a region known as the local bubble, a cavity of hot, low-density gas thought to have been created by ancient supernova explosions. Surrounding this bubble are denser clouds of gas and dust, some of which are now being studied in greater detail with infrared observations. Understanding the structure of these nearby clouds helps astronomers reconstruct the recent history of our galactic neighbourhood, including past supernova events and the movement of gas through the Orion Spur. There is something quietly fascinating about realising that the space around us is not empty, but filled with structures, bubbles, filaments, and clouds, each with its own history and motion. Webb's observations are also refining our understanding of the vertical structure of the galactic disk. Stars and gas are not confined to a perfectly flat plane. There are ripples, waves, and vertical motions caused by gravitational interactions and past events such as the passage of satellite galaxies. By studying star-forming regions at different heights above and below the galactic plane, astronomers can better understand how these structures are distributed and how the disk evolves over time. This contributes to a more accurate three-dimensional map of the Milky Way, one that includes not only positions in the plane but also vertical structure. Another subtle but important refinement involves the boundaries of the Orion Spur itself. The spur is not a sharply defined structure with clear edges. It is a complex region where gas, stars and clusters form a network that gradually blends into neighbouring spiral arms. By mapping star-forming regions and molecular clouds with greater precision, Webb is helping astronomers trace the contours of this structure more accurately, improving our understanding of how it connects to the Sagittarius and Perseus arms. These refinements may seem technical, but they have a broader significance. Knowing our position within the galaxy is not just about coordinates. It is about understanding the environment in which the solar system formed and evolved, the distribution of gas and dust, the frequency of nearby supernova, the rate of star formation in our region. All of these factors influence the conditions in which planetary systems develop. In that sense, refining the map of the Milky Way is also refining our understanding of the context of life on Earth. There is something quietly grounding about that realization. We often think of ourselves as isolated on a small planet, but in reality we are part of a much larger system, a system that has a history, a structure, and an ongoing evolution. Webb's contributions are helping us see that system more clearly, not by making dramatic announcements that overturn everything we thought we knew, but by improving the precision of our measurements, filling in gaps, and revealing details that were previously hidden. Science often advances in this way, through careful refinement rather than sudden revolution. Each new observation reduces uncertainty, each improved measurement sharpens the picture, and over time the map becomes clearer. If you could watch the Milky Way from far above, not for a few minutes or even a few years, but for millions of years at a time, you would notice something that the night sky never reveals to the casual observer. The galaxy is not still. It is in constant motion, a vast, slow choreography of stars, gas and dark matter, all moving together yet each following its own path. From Earth, the sky appears steady. Constellations hold their shapes for generations, and the Milky Way arches overhead in the same familiar pattern night after night. But this apparent stillness is an illusion created by timescale. Human lives are short compared to the rhythms of a galaxy. Changes that are dramatic over millions of years are imperceptible in a single lifetime, and yet those changes are happening all the time, quietly, steadily, shaping the structure of our home. The first and most fundamental motion is rotation. The Milky Way rotates, with stars orbiting the galactic centre much as planets orbit the Sun. But the motion is not like a rigid wheel turning. Different parts of the galaxy move at different speeds, and the rotation is governed not only by the visible matter we can see, but also by a vast halo of dark matter that surrounds the galaxy and contributes to its gravitational pull. Our Sun, as you've heard before, travels at roughly 220 kilometers per second around the centre of the galaxy. That speed is difficult to grasp, yet even at that pace, the orbit takes about 230 million years to complete. A single galactic year is longer than the time that has passed since the earliest dinosaurs appeared on Earth. While the Sun follows its orbit, so do countless other stars, each on its own path. Some move slightly faster, some slightly slower, and their orbits are not perfectly circular. Over time, stars drift relative to one another, changing their positions gradually. If you could compress millions of years into a few seconds, the constellations would stretch, twist, and dissolve, forming entirely new patterns. Astronomers can actually measure this motion. By observing the positions of stars with extreme precision over many years, missions like Gaia have detected tiny shifts, the slow drift of stars across the sky known as proper motion. These measurements allow scientists to reconstruct the trajectories of stars and understand how different parts of the galaxy move. But rotation alone does not explain the structure of the Milky Way, especially its spiral arms. For a long time, astronomers wondered how spiral arms could persist. If the arms were made of the same stars over long periods, differential rotation would quickly wind them up tightly, like cream stirred into coffee. Yet spiral patterns remain visible in many galaxies, including our own. The explanation lies in the concept of density waves. Spiral arms are not fixed collections of stars moving together. They are regions of higher density, waves of gravitational influence that move through the disk of the galaxy. As gas and stars orbit the centre, they pass through these denser regions, much like cars moving through a traffic jam. The traffic jam itself can persist even though the individual cars enter and leave it. When gas clouds enter a spiral arm, they are compressed by the increased density. This compression can trigger star formation, leading to the bright clusters of young stars that illuminate the arms. Over time, those stars drift away, while new ones form as fresh gas enters the region. This means the spiral arms are patterns rather than permanent structures, shaped by the dynamics of the galaxy as a whole. Understanding this motion has been one of the great achievements of modern astronomy, combining observations, simulations, and theoretical models to explain how spiral galaxies maintain their shapes over billions of years. But rotation and spiral density waves are only part of the story. The Milky Way is also interacting with its surroundings. Our galaxy is not alone in space. It is accompanied by dozens of smaller satellite galaxies, some of which are slowly being pulled apart by the Milky Way's gravity. Streams of stars, the remnants of these interactions, have been detected stretching across the sky, evidence of past encounters that have left their mark on the galaxy's structure. One of the most prominent of these companions is the Sagittarius dwarf galaxy, which is currently being disrupted as it orbits the Milky Way. Over time, its stars are being stripped away, forming long tidal streams that wrap around the galaxy like faint ribbons. These interactions are not violent on human timescales, but over millions and billions of years they reshape the galaxy, altering the distribution of stars and gas and even affecting the structure of the disk. There is also evidence that the Milky Way's disk is not perfectly flat. Observations have revealed ripples and waves in the distribution of stars, subtle distortions that may have been caused by past encounters with satellite galaxies. These waves propagate slowly through the disk like ripples spreading across the surface of a pond after a stone has been dropped. The galaxy, in other words, is not a rigid object. It is flexible, responsive, constantly adjusting to the gravitational influences around it. And then there is the motion of the galaxy itself through space. The Milky Way is part of a larger structure known as the Local Group, a collection of more than 50 galaxies bound together by gravity. Within this group, galaxies move relative to one another, slowly drifting and interacting over billions of years. The most significant of these motions involves the Andromeda Galaxy, our nearest large galactic neighbour. Observations show that Andromeda and the Milky Way are moving toward each other at about 110 kilometers per second. In roughly 4 to 5 billion years, the two galaxies are expected to merge in a slow, graceful collision that will reshape both of them into a new, larger galaxy. It is important to understand that this collision will not resemble two solid objects crashing together. The stars in galaxies are so widely spaced that direct collisions between stars are extremely unlikely. Instead, the galaxies will pass through one another, their gravitational fields distorting their shapes, triggering waves of star formation and gradually blending their stellar populations. By the time this happens, the Sun will be nearing the end of its life, and Earth, if it still exists, will be a very different world. These events unfold on timescales far beyond human history, yet they are part of the long-term evolution of our galaxy. Closer to home, the interstellar medium, the gas and dust between stars, is also in motion. Gas clouds drift through the galaxy, sometimes colliding and merging, sometimes dispersing under the influence of stellar winds and supernova explosions. These processes recycle material, enriching the interstellar medium with heavy elements forged in the cores of stars. Every atom of carbon in your body, every atom of oxygen you breathe, was once part of this cycle, formed in ancient stars and scattered into space before becoming part of new stars and planets. The Milky Way is not just a collection of stars, it is an ecosystem of matter and energy, constantly renewing itself. The James Webb Space Telescope is contributing to our understanding of this evolution, by observing star-forming regions, measuring the composition of gas clouds, and studying the environments where new stars are emerging. These observations help astronomers trace how material moves through the galaxy, how star formation proceeds, and how the structure of spiral arms changes over time. Webb's ability to peer into dusty regions allows scientists to observe the earlier stages of star formation, capturing moments that were once hidden. By studying these regions, astronomers can better understand how the galaxy transforms gas into stars, and how those stars, in turn, influence their surroundings. There is something quietly profound in realizing that the Milky Way is not a finished structure. It is still evolving, still forming stars, still interacting with its neighbours, still changing in ways that are subtle but continuous. And all of this motion is happening while we go about our daily lives, while cities sleep and wake, while seasons change, while generations come and go. The galaxy turns, indifferent to our timescales, yet carrying us along with it. It can be comforting in a way to imagine that steady motion. The Earth spins, the Earth orbits the Sun orbits the centre of the galaxy, and the galaxy itself moves through the universe, layers upon layers of motion, each unfolding at its own pace, each part of a larger whole. And within that vast movement, the solar system follows a particular path, not only around the galactic centre, but also through different regions of the galaxy over time. If the Sun is orbiting the galaxy, what does that journey look like, and what kinds of environments has our solar system passed through, and will pass through again, as it continues its slow, silent voyage around the galactic centre? Although the night sky appears steady and unchanging, the solar system is quietly travelling through the Milky Way, carried along in an immense orbit that began billions of years ago and will continue long after our species is gone. It is easy to forget this motion because we cannot feel it. There is no wind of stars rushing past, no sense of acceleration, no visible landmark sliding by from one year to the next. The distances are simply too vast, and the timescales too long for motion to be obvious. Yet the journey is real. The Sun, along with its planets, follows a path around the centre of the galaxy at roughly 220 kilometers per second. That speed is almost unimaginable in everyday terms. At that pace, you could circle the Earth in under 3 minutes. But the orbit itself is so enormous that even at that speed, completing one circuit takes about 230 million years. Astronomers sometimes call this a galactic year, and it gives an interesting perspective on time. The solar system formed about 4.6 billion years ago, which means the Sun has completed only around 20 orbits of the Milky Way in its entire lifetime. The Earth has existed for roughly the same span, and all of human history occupies only a tiny fraction of a single galactic year. If you could speed up time and watch the solar system from far above the galaxy, you would see it tracing a long, slow arc through the disk, passing through regions of differing density, different stellar neighbourhoods, and varying environments of gas and dust. This motion is sometimes compared to the changing of seasons, though on a scale so vast that the analogy is only loosely accurate. As the solar system orbits, it moves closer to or farther from spiral arms, passes through regions where star formation is more or less active, and encounters different conditions in the interstellar medium. Spiral arms, as you've heard, are not fixed structures. They are patterns of higher density moving through the galaxy. Stars drift in and out of them over millions of years. There is evidence that the solar system has passed through spiral arms in the distant past, though reconstructing the exact path is challenging because the arms themselves evolve over time. Passing through a spiral arm can have noticeable effects on the local environment. These regions contain more gas, more dust, and more massive stars, which means higher rates of supernova explosions. Supernova release enormous amounts of energy and can influence nearby gas clouds, triggering new star formation or altering the conditions in surrounding space. Some scientists have explored the possibility that past passages through spiral arms may have influenced Earth's climate or biological history, perhaps by increasing the rate of nearby supernovae and the amount of cosmic radiation reaching the planet. This idea remains an area of ongoing research, and the evidence is still being debated, but it illustrates how our galactic environment may change over time. Even outside spiral arms, the solar system is not travelling through empty space. The interstellar medium, the thin gas and dust between stars, varies in density and composition. At present, the Sun is moving through a region known as the local interstellar cloud, a relatively sparse cloud of gas that lies within a larger cavity called the local bubble. The local bubble is thought to have formed from a series of supernova explosions millions of years ago. These explosions cleared out much of the gas in the region, leaving a volume of hot, low-density plasma surrounded by denser clouds. As the solar system moves, it gradually drifts through these structures, though the changes occur so slowly that they are imperceptible on human timescales. Another aspect of the Sun's motion is its gentle oscillation above and below the galactic plane. The solar system does not remain at a fixed height within the disk. Instead, it moves in a slow wave, rising and falling over tens of millions of years, crossing the midplane periodically. This vertical motion is caused by the gravitational pull of the disk itself. As the Sun moves slightly above the plane, gravity pulls it back downward. As it passes through the plane, it continues downward for a while, before gravity slows and reverses the motion. The result is a smooth oscillation, like a buoy rising and falling on gentle swells. Some researchers have suggested that these crossings of the galactic plane might correlate with certain events in Earth's geological record, though this remains speculative. The timescales involved are long, and many factors influence conditions on Earth, so drawing direct connections is difficult. Still, the idea that our planet's environment might be influenced even subtly by our position in the galaxy is a fascinating one. There is also the matter of nearby stars. The Sun does not travel alone. It is part of a moving group of stars that share similar velocities and may have formed in the same region long ago. Over time, gravitational interactions gradually disperse such groups, but traces of their shared motion can still be detected. Astronomers can reconstruct some of this history by studying the motions and compositions of stars near the Sun. Stars with similar chemical signatures and trajectories may once have been part of the same cluster, long since dispersed across the galaxy. In this way, the solar system's journey is not just a path through space, but a story of origins and migrations, of clusters forming and dissolving, of stars drifting apart over millions of years. The James Webb Space Telescope contributes to this understanding by studying star-forming regions and young clusters, helping astronomers learn how stars are born in groups and how those groups evolve. By observing clusters at different ages, scientists can trace the processes that eventually lead to stars like the Sun becoming isolated from their birth environments. There is something quietly meaningful in realizing that the Sun was not always alone. It likely formed in a cluster of hundreds or thousands of stars within a dense molecular cloud. Over time, gravitational interactions and the motion of the galaxy dispersed that cluster, leaving the Sun to orbit the galaxy largely on its own, accompanied only by its planets. That process is still happening elsewhere in the Milky Way. Clusters are forming, evolving and dispersing, adding new stars to the galaxy's disk. Looking ahead, the solar system's journey will continue. Over the next tens of millions of years, it will drift into new regions of interstellar space, encounter different clouds of gas and dust, and gradually change its position relative to spiral arms. On even longer timescales, the structure of the galaxy itself will change. Spiral arms may shift, star formation rates may vary, and interactions with satellite galaxies will continue to reshape the disk. And far in the future, billions of years from now, the Milky Way and the Andromeda Galaxy will begin their slow merger, transforming the entire structure of our galactic home. But for now, the solar system moves quietly along its orbit, one small path among billions, carried by gravity through a vast and slowly changing environment. It can be calming to imagine that motion, to picture the Sun gliding through the galaxy, the planets circling steadily, the stars around us drifting in their own paths. The journey is continuous, unhurried, unfolding on timescales so long that it feels almost timeless. What does it actually mean to live in a spiral arm, or in our case, a spur between arms? And how does that environment shape the conditions around us, from star formation to the long-term stability of planetary systems like our own? When astronomers describe our location in the Milky Way, saying that we live in the Orion spur between two larger spiral arms, it can sound like a simple geographic label, almost like giving the name of a district in a city. But that description carries deeper meaning, because spiral arms are not just shapes drawn on a map. They're environments, regions where the density of stars, gas and dust differs from one place to another, where conditions can influence how stars form and how planetary systems evolve. To understand what it means to live in a spiral arm, or in our case a smaller spur connected to larger arms, it helps to think again about how spiral structure works. Spiral arms are regions where material in the galactic disk becomes slightly compressed as it moves through density waves. Gas clouds entering these regions are squeezed, and that compression often triggers star formation. Massive, bright stars are born in clusters, lighting up the surrounding gas and making the arms visible across great distances. Because of this, spiral arms tend to be rich in young stars, nebulae, and molecular clouds. They are active places, regions where new stars are constantly being created, but they are not uniformly crowded. Even within a spiral arm, there are quieter pockets and denser complexes, just as a city has both busy neighbourhoods and calm residential streets. The Orion spur is one of those quieter regions, less densely packed than the major arms, but still rich enough in gas and stars to support ongoing star formation. Our position here appears to offer a kind of balance. If the solar system were located much closer to the galactic centre, the environment would be very different. The inner regions of the Milky Way are crowded with stars, and gravitational interactions are more frequent. Massive stars, which live short and violent lives, are more common there, and supernova explosions occur more often. A nearby supernova can affect planetary systems, potentially stripping atmospheres or altering climates through increased radiation. While such events are rare on human timescales, they become more probable in densely populated regions of the galaxy. Farther out in the galaxy, beyond the main spiral structure, the situation changes again. The density of gas decreases and the rate of star formation drops. There are fewer heavy elements because those elements are produced in stars and dispersed by supernova explosions over time. Regions with fewer heavy elements may be less likely to form rocky planets like Earth. This leads to the idea of a galactic habitable zone, a region of a galaxy where conditions may be favourable for the development of complex life. It is not a sharply defined band, and it depends on many factors, but our location in the Orion spur appears to fall within this broader zone. We are far enough from the crowded centre to avoid frequent catastrophic events, yet close enough to regions of star formation to have inherited a rich supply of heavy elements, the carbon, oxygen, silicon and iron that make up planets and living organisms. There is something quietly reassuring about that realization. Our position is not special in the sense of being central or unique, but it may be well suited to the long-term stability that life requires. Another aspect of living in a spiral arm environment is the presence of molecular clouds, vast cold regions of gas and dust where new stars are born. These clouds are not evenly distributed. They tend to cluster along spiral features, marking regions where the density of material is higher. Some of these clouds are relatively close to us in galactic terms, a few hundred or a few thousand light-years away. The Orion Molecular Cloud Complex, for example, contains the Orion Nebula and several other star-forming regions, all part of the same larger structure. Observing these regions provides insight into the processes that shape stellar and planetary systems. The James Webb Space Telescope, with its ability to see through dust, has been revealing the fine structure of such clouds, showing filaments, dense cores, and newborn stars embedded within them. These observations remind us that star formation is not a distant phenomenon. It is happening in our neighbourhood right now, in clouds that are part of the same spiral feature that contains the Sun. At the same time, the distances involved are still immense. Even the nearest star-forming regions are hundreds of light-years away, far beyond any possibility of direct influence on Earth in the foreseeable future. Another characteristic of spiral arms is the presence of massive stars, hot, luminous stars that burn their fuel quickly and end their lives in supernova explosions. These stars are relatively rare, but they play an important role in enriching the interstellar medium with heavy elements and in shaping nearby gas clouds through their winds and radiation. Our immediate neighbourhood contains relatively few massive stars compared to the inner regions of the galaxy, which contributes to the stability of our environment. The nearest known supernova candidates are far enough away that they pose no immediate threat, and the rate of such events in our region is relatively low. There is also the matter of radiation and cosmic rays. Spiral arms, with their higher rates of star formation and supernova explosions, tend to have higher levels of energetic radiation. While Earth's atmosphere and magnetic field provide strong protection, prolonged exposure to intense radiation could affect planetary environments. Being in a quieter part of a spiral feature reduces that risk. Another subtle influence of our galactic environment involves gravitational disturbances. In crowded regions, close encounters between stars are more likely. Such encounters can perturb the outer regions of planetary systems, potentially altering the orbits of comets and asteroids, or even destabilizing planets over long timescales. In our region, the average distance between stars is large enough that such encounters are extremely rare. The nearest star, Proxima Centauri, is more than 4 light-years away, and most stars are much farther. The solar system moves through a relatively open region, with ample space between stellar neighbours. This does not mean the environment is completely empty. The solar system passes through variations in the density of interstellar gas and dust, and these changes can affect the heliosphere, the bubble of charged particles created by the solar wind that surrounds our system. Over very long periods, such changes may influence the influx of cosmic rays, or the distribution of interstellar material near the outer reaches of the solar system. These effects are subtle and gradual, but they are part of the broader context of our journey through the galaxy. The Orion Spur itself is an interesting structure. It appears to be a bridge between the Sagittarius arm and the Perseus arm, containing a mixture of young stars, molecular clouds, and older stellar populations. Mapping its full extent has been challenging, but modern surveys, including infrared observations and precise distance measurements from missions like Gaia, are gradually revealing its shape and boundaries. The James Webb Space Telescope is contributing by studying star-forming regions within the spur, providing detailed observations of the environments where new stars are being born. These observations help refine our understanding of how the spur connects to the larger spiral arms and how material flows through these structures. There is something quietly fascinating about realizing that our galactic neighborhood is not static, but part of a larger pattern shaped by gravitational forces, waves of density, and the life cycles of stars. And yet, despite all this activity, the environment around us remains remarkably calm on human timescales. The night sky changes slowly, the nearest stars drift imperceptibly, and the Milky Way continues its steady rotation. It is easy to feel small when thinking about these scales, but there is another way to look at it. We are not separate from the galaxy. We are part of it, made of the same elements forged in ancient stars, orbiting within one of its spiral features, carried along in its slow, continuous motion. Understanding our environment within the Milky Way is not just about knowing our address. It is about understanding the context in which our planet formed, the conditions that allowed life to emerge, and the broader system of which we are a part. After spending time understanding where we are in the Milky Way, it is natural for the mind to pause and ask a broader question. If our solar system is only a tiny part of a spiral arm, and that spiral arm is only a small feature within a single galaxy, what does that mean when we look beyond the Milky Way itself? This is where perspective begins to shift again, much as it did when astronomers first realised that Earth was not at the centre of the solar system, and later that the solar system was not at the centre of the galaxy. Each step outward changes the scale of the picture, and with each change, familiar things seem smaller, but the universe becomes richer and more interesting. The Milky Way, vast as it is not alone in space. Even with small telescopes, astronomers in the early 20th century began to realise that some faint, fuzzy objects in the sky were not clouds or nebulae within our galaxy, but entire galaxies of their own, each containing billions or even trillions of stars. Today, we know that the observable universe contains hundreds of billions of galaxies, perhaps more, scattered across unimaginable distances. To picture this, it can help to think again in terms of scale. If the Milky Way were reduced to the size of a coin, the nearest large galaxy, Andromeda, would be several meters away. Beyond that, other galaxies would be scattered across distances measured in kilometers, and the observable universe would stretch far beyond any horizon you could see. And yet, despite those enormous separations, galaxies are not randomly distributed. They tend to gather in groups and clusters, bound together by gravity. Our galaxy belongs to a small collection called the Local Group, which contains more than 50 galaxies. Most of these are small dwarf galaxies, faint and irregular, but two large spirals dominate the group, the Milky Way and Andromeda. There is also a third significant member, the Triangulum galaxy, smaller but still substantial. These galaxies are bound together by their mutual gravity, drifting slowly through space in a long, gradual dance that unfolds over billions of years. As you heard earlier, the Milky Way and Andromeda are moving toward each other and will eventually merge, forming a new galaxy far in the future. But the Local Group itself is only a tiny part of a much larger structure. Galaxies gather into clusters, and clusters gather into superclusters, vast regions containing thousands of galaxies connected by gravity and dark matter. Our Local Group lies within a region known as the Virgo supercluster, which itself is part of an even larger structure called Laniakea, a vast collection of galaxies spanning hundreds of millions of light-years. These structures are not solid or sharply defined. They are more like currents in an ocean, regions where galaxies are slightly more concentrated, flowing slowly under the influence of gravity. When astronomers map the distribution of galaxies on the larger scales, they see something remarkable. Galaxies are not spread evenly through space. Instead, they form a vast cosmic web, filaments of matter stretching across enormous distances, with clusters of galaxies at the intersections and enormous voids in between where relatively few galaxies exist. This web-like structure is shaped by gravity acting over billions of years, drawing matter together into patterns that are only now becoming clear through large surveys and detailed observations. There is something quietly astonishing about realizing that the Milky Way is not just part of a galaxy group, but part of a filament in a cosmic web that spans the observable universe. And yet even this immense web is only the portion of the universe we can see. Beyond the observable universe, space may continue indefinitely, or it may have a structure we cannot yet detect. The limits of observation are set by the speed of light and the age of the universe, meaning there are regions so distant that their light has not had time to reach us since the beginning of cosmic expansion. When you think about these scales, it becomes clear why astronomers sometimes describe the universe as humbling. Not because smallness diminishes us, but because it places our existence in a broader context. Every person who has ever lived has done so on a small planet orbiting an ordinary star, located in a minor spur of a spiral galaxy, itself one of billions, all embedded in a vast cosmic web. And yet, there is another side to this perspective that is easy to overlook. We are small in size, but not in awareness. The atoms that make up our bodies were formed in ancient stars, forged in stellar cores and scattered by supernova explosions long before the sun existed. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were created in processes that unfolded across the galaxy over billions of years. In that sense, we're not separate from the universe. We're part of its history, part of its ongoing story. There is something quietly comforting in that thought. The same laws of physics that shape distant galaxies also shape the atoms in your body. The same gravity that guides the motion of stars holds your feet to the earth. The same light that travels across the universe enters your eyes when you look at the night sky. When telescopes like the James Webb Space Telescope observe distant galaxies, they are not only revealing the universe's past, but also helping us understand our own origins. Many of the elements essential to life were formed in the first generations of stars in galaxies that existed billions of years before the Milky Way reached its present form. Webb's observations of distant galaxies show us how stars formed in the early universe, how galaxies grew and evolved, and how the chemical elements necessary for planets and life were produced and distributed. In a way, these observations connect the larger scales of the universe to the smallest details of our existence. There is also a psychological aspect to this broader perspective. When people first learn about the scale of the universe, it can feel overwhelming. Distances measured in millions or billions of light years can seem almost abstract, too large to grasp in a meaningful way. But if you approach these ideas slowly, the way we have been doing tonight, they begin to feel less intimidating and more calming. The universe is vast, but it is also orderly. Galaxies follow predictable motions. Stars form according to physical laws that can be studied and understood. Even the expansion of the universe follows patterns that astronomers can measure with remarkable precision. There is a quiet stability in that order, a sense that the universe is not chaotic in the everyday sense, but governed by consistent principles that operate everywhere. And within that vast and orderly system, there is room for small things to matter. A single planet can support life. A single species can develop curiosity and build instruments capable of studying galaxies billions of light years away. A single mind can contemplate the structure of the universe while lying in a quiet room at night. That contrast between the immense scale of the cosmos and the intimate scale of individual experience is one of the most remarkable aspects of being human. When you look up at the Milky Way, you're seeing only a tiny fraction of what exists. Beyond that pale band lie countless galaxies, each with its own spiral arms, star clusters and planetary systems. Some of those galaxies are so distant that their light began travelling toward us before the Earth formed. And yet, all of that vastness is connected by the same physical laws, the same processes of gravity, fusion and motion that shape our own galaxy. Understanding our place in the universe does not diminish our significance. Instead, it provides context, a way of seeing ourselves as part of a much larger story, one that began long before we arrived and will continue long after. There is something calming in that realization. The worries of a single day, the small frustrations and concerns that fill our thoughts, exist within a universe that is patient, vast, and unhurried. Stars form, shine, and fade. Galaxies drift and merge. The cosmic web evolves slowly, over timescales that make human history seem like a brief moment. And yet, that brief moment is enough for us to observe, to learn, and to wonder. Now, after travelling in thought from the surface of Earth to the scale of the Milky Way, and then outward to the wider universe beyond it, it can be nice to let the mind slow down again, to return gently to something familiar. If you were to step outside tonight, or perhaps imagine doing so, the sky would not look very different from the way it has always looked. The same stars would shine, the same constellations would hold their shapes, and if the sky were dark enough, the Milky Way would still stretch across the darkness as a pale, quiet band. Nothing in the sky announces the distances you've been thinking about. There are no labels marking spiral arms, no lines tracing our orbit around the galactic centre, no signs pointing toward the Orion spur. All of that knowledge exists quietly in the background, something we carry in our understanding rather than something we see directly. And yet, once you know it, the sky never feels quite the same again. That faint band of light is no longer just a beautiful pattern. It is the combined glow of hundreds of billions of stars arranged in a vast rotating system, one that our sun has been orbiting for billions of years. It is a reminder that we are not just looking at the universe, but living inside it. For most of human history, people looked up and wondered what the Milky Way was. They imagined rivers of light, roads of spirits, trails of milk scattered across the heavens. Those stories were ways of making sense of something mysterious, ways of connecting human experience to the vastness overhead. Today, our understanding is different, but the sense of wonder remains. We know that the Milky Way is a spiral galaxy, that our sun lies about 26,000 light-years from the centre, that we are moving through the Orion spur at extraordinary speed, carried along in a slow orbit that takes hundreds of millions of years to complete. We know that stars are forming in distant clouds of gas, that spiral arms are shaped by waves of gravity, that the galaxy itself is part of a larger group of galaxies drifting through space. And thanks to telescopes like the James Webb Space Telescope, we are seeing these processes more clearly than ever before, looking into dusty regions where new stars are born, refining our map of the galaxy, and learning more about the environment that surrounds us. But even with all of that knowledge, the night sky retains its quiet simplicity. A handful of bright stars, a faint glow of distant light, a feeling of stillness. There is something comforting about that contrast, the difference between what we see and what we know. The universe is vast and dynamic, yet from our small corner of it, it often feels calm and steady. Perhaps that is why looking at the stars has always been soothing. The sky moves slowly. The patterns change gently over the seasons. The Milky Way rises and sets year after year as it has for thousands of years. It gives a sense of continuity, a reminder that while human life is brief, it unfolds within a universe that is patient and enduring. And there is another thought worth carrying with you. Every atom in your body was once part of a star. The carbon that forms the structure of your cells, the oxygen you breathe, the iron in your blood, all were forged in stellar furnaces long before the sun existed. Those atoms travelled through space, became part of a cloud of gas and dust, and eventually became part of the Earth, and of you. In that sense, when you look up at the Milky Way, you're looking at something you're made of, not metaphorically, but literally. It is easy to feel small when thinking about the scale of the universe, but there is another way to see it. We are small, yes, but we are also connected to everything around us. The same physical processes that shape galaxies also shape the atoms that make up our world. We are part of the story, not separate from it. And perhaps that is the most peaceful thought of all. The universe is not something distant and unreachable. It is the environment in which we exist, the larger home that contains our smaller one. As you settle in, wherever you're listening, you might imagine the solar system continuing its slow journey around the galaxy, the sun gliding through the Orion spur, the Milky Way turning gently, the stars drifting in their long, silent orbits. All of it moving, all of it unfolding whether we notice it or not. And here, on this small planet, in this quiet moment, you are part of that motion, carried along with everything else, surrounded by a universe that is vast, ancient, and, in its own way, deeply calm. So the next time you see the night sky, or even just picture it in your mind, you may remember that the faint band of the Milky Way is not just something far away. It is home, our place in a galaxy of unimaginable scale, a small corner of a much larger universe gently turning in the dark.